Okay, now it has started. I will paste the link. Okay. So this is the link. Okay, so I have pinned it. You can see it. Okay.
Okay, okay.
Okay, so we will start in 5 minutes. We will wait for others to join, then we will start. Okay, so yeah, tomorrow timing will be same. Okay. Uh, okay. So for those who have joined just now, we will be starting with PYQ session, PYQ for week 5 and 6. Okay. And while discussing the question, we will also discuss important concepts related to week 5 and 6. Is this clear? Um, and one more thing, is my voice clear?
Yes, sir.
Yes, it's clear.
Okay, fine. Okay, and week 7 and 8 will be covered in tomorrow's session. Okay. Okay, so let's start. Sorry. Okay, so can you see my screen now?
Yes, it's visible.
Okay, so let's start. Okay, so okay, can you see my pointer, my mouse pointer? Can you see it?
No, sir.
Not. Can you
No,
see
that
it
is
now?
not visible.
Okay. Can you see this hand symbol? No. Can you see my notebook?
Yes, sir.
Yeah, the
Sir,
notebook is
sir,
visible.
try to write something. Try to write something. Maybe we can see
Okay.
that. that-
Fine. So
Yeah,
yeah.
And
now
now
it's
it's visible.
Yeah, the cursor is visible. Yeah.
Okay. Okay. So here. So okay. So let's start. So before starting, let's do one thing. Let's do a revision of some basic. Okay. So uh, okay. Fine. Yeah. So you know that a linear transformation, a linear transformation has this property, right? Which is f of v1 plus v2 is equals to f of v1 plus f of v2. Okay. So suppose there is a linear transformation from one vector space to another vector space. Okay. Then it will be a linear transformation if this condition is satisfied. Now, corresponding to every linear transformation, there is a matrix associated with it, right? And this matrix need not be unique. There are infinite such matrices, right? If you keep on changing the ordered basis of domain, so that is, if you change the ordered basis for domain and for domain, you will get different such matrices, right? Are you clear with this? Is this clear?
Yes,
Hello?
it's clear.
Okay, so these matrices are not unique. You know that every matrix is with respect to a ordered basis for domain as well as codomain. So there are matrices. Okay, so every linear transformation has a matrix associated with it. Now, okay, okay, when linear transformation is 1 1, when if f of v is equals to 0 implies v is equals to 0. Okay, if f of v on being equated to 0 implies that v was 0, then f is 1 1. Okay, a linear transformation is onto if for all w, okay, small w belongs to capital W, that is for all vectors belonging to your codomain. So this is your domain and this is your codomain. Okay, so a linear transformation is onto if for all w in capital W, that is your codomain vector space, there exists v belongs to your domain such that f of v f of v f of v, tell me.
is equal to W.
Yeah. Okay, so this is what is meant by onto. Now what is the actual definition for 1 1? This is the alternate definition, if you remember. What is the actual definition for 1 1? You,
Different inputs map to different outputs and
yeah.
same
If
inputs map
if
to same
if
outputs.
if no input, if no two inputs are mapped to same output, right? Yes or no? Okay. So this is your alternate definition. Okay. What is the original
Sir, can
definition
you
of?
give an example for on to, sir?
Yeah, we will see all of those. Okay, so but just for now, remember that a linear transformation is on to if for all. So see, basically what this is saying is, this means that range is equals to codomain, right? This is what is meant by onto. Range is equals to codomain. So this is your codomain. Suppose there are only 5 elements in it, and here there are 5 elements. Okay, so suppose there is a mapping f from this domain to codomain. Now see, now can you tell me what is the range of this f? Is it only this much?
First four element of codomain set.
Yeah, only this is codomain. So in this case, f is not onto. Okay, and is not onto, since this element does not have any pre-image in domain. Okay, now this is not onto.
So,
Okay, these are just basics I am revising. We will see how we will solve it in case of linear transformation. But
so
again, the
sir,
concepts are same. Yeah,
uh, we say onto if range is equal to codomain, right?
yeah.
So if
So
if
here,
the dimension,
see here range is only, yeah, right now we are not talking in terms of linear transformation. I'm just revising the maths one concept. So you can see that range only has 4 elements while codomain has 5 elements. So you can see range is not equal to codomain. So that's why this is not onto function. Is this clear?
so
Now,
so the dimension of the column space or row
yeah.
space is the
See,
range, right?
we will move on to that. For just now,
Okay,
I'm
okay.
revising the maths one. So what is 1 1? 1 1 is if no two inputs are mapped to same output. Now can you tell me whether this is 1 1?
Yes, sir, it is one one.
Are you
No,
sure?
No, no.
This is not
No,
1
No,
1.
it's
sir.
not.
it's not one one.
It's many
Two
one.
elements are mapped
Yeah,
to
No,
same
it's not
yeah,
one
object.
one.
because
It's
see,
that.
yeah, these two elements are mapped to the same output. So this is not 1 1. Okay. Now, okay, fine. Okay, so uh, fine. I think you are clear with the 1 1 and on 2 part. Now uh, let's see in terms of linear transformation. So what is meant by 1 1 and what is meant by on 2, and what does this alternate definition actually means? Okay. So suppose we are suppose we have this f from R3 to R3. Okay. Now what is your input domain? First of all, tell me what is your input domain? Is it R3?
Yes.
Yes, sir.
What is your output codomain?
R3.
Now, okay, fine. So suppose I define this. Yeah, go on. Go on. Anyone was saying something? No? Okay. Okay. Yeah. So suppose this is your linear transformation. Okay. X plus y, x minus y, 2x plus 3y. Suppose this is a linear transformation. Sorry, z, I forgot z. Okay. Suppose this is a linear transformation. Now, first of all, see, the thing is, when what types of question can be asked in this? Linear transformation will be given such definition, and they will ask you these types of questions. Question one is rank of this linear transformation. Then question two is nullity. Then question three is onto. Question four could be asked is 1 1. Then it can be asked whether it is an isomorphism. Okay,
So
isomorphism.
basis
Basis what? Sorry.
for some image or kernel.
Yeah. So isomorphism. Okay. So isomorphism. Oh yeah, isomorphism is another name for bijection. Okay. So are you aware that what is bijection?
Sir, both 1 1 and on 2.
Yeah, exactly. Okay. Then they can ask you what is range. Okay. Slash image set. Okay. Then question 7 is uh, kernel. Then another name for kernel is nothing but null space, right? So all these types of questions will be asked. Okay, so most of the questions will be revolving around these only. Are Is it clear? Now how do we okay, so using this definition to answer all these is not feasible, right? So what, you know that every linear transformation, okay, every linear transformation has a corresponding matrix. Okay, so every linear transformation has a corresponding matrix. Now if you somehow can get hold of this matrix, you can answer all of these at once. Okay, and most of the questions will be revolving around these only, and you will see that in the PYQ. Okay, so okay, so this is one point, that every linear transformation has a corresponding matrix. If you get a hold of this matrix, you can answer each of these. Now,
Sir, will it be given?
no, this is not given. You will have to find it. So how we find it?
So
So
we can directly
yeah. So basically, what
take
you have to do, yeah. So to find the corresponding matrix, find the basis for input domain. Find your standard input domain basis. Okay. Find your input domain basis. So what is your input domain in this case? Tell me. Is it R3? Is it R3?
Yes.
Okay. Now, what is the standard basis for R3?
1 0 0 0 1 0 0 0 1.
Yeah. Yeah. Okay. Uh, mm, fine. 1 0 0 0 1 0. Is it visible, or are you having any problem? Should I zoom in?
Yes, sir, it's well.
Okay. So 1 0 0 0 0 1. Okay. Now what you will do? You will just read. Okay. Now what you will do, you will feed these vectors. You will feed these vectors from the input domain basis vector set into this linear transformation, which has been defined for you. Okay, to get the whole of the matrix. So what you will do, you will find the image of first. So according to this, what is the image according to this definition? It is x plus y, x minus y, 2x plus 3y minus z, right? So it is x plus y, so 1 plus 0, 1, then x minus y, so 1 minus 0, 1, then 2x plus 3y minus z. So 2, okay, so it would be 2, right? 2x, 2 into 1 plus 3y minus z. So 3 into 0 minus 0. So this will give you 2. So you have got your one image. Then 0, 1, 0. That is the second vector's image. So you will find it. What is it? It would be x plus y. So 0 plus 1, 1. Okay. Then x minus y. So minus 1. Then 2x plus 3y minus z. So 2 into 0 plus 3y minus z. So 3. Okay, from this again I am repeating, I am using this. Okay, let me zoom out so you
What
can
you
see
have
it.
written in the first line, every LT has a corresponding matrix. Can you read it
Yeah,
just once?
every linear transformation has a corresponding matrix associated with it. Okay,
Okay. Yeah, got it.
now last vector from this set, this will be uh, x plus y, so 0, 0, then minus 1. So now you will just place these 1, 1, 2. So you will place these outputs in a matrix as columns 0, 0, minus 1. So now you have got your
Corresponding
uh,
matrix.
yeah, corresponding matrix. Now once you get a hold of this, you can answer each of these questions. So to answer this, you have to convert. Right now the work is not complete. You have to convert A1 to its REF form. So let's convert it. 1, 1, 0, 1 minus 1, 0, 2, 3 minus 1. So we start from the top left corner. This is a pivot. It is 1. So we need not scale it. So it is 1. Now we start cleaning down, right? So 1, 1, 0. So what we will do, we will subtract it. Subtract R2, R1. Okay. So this will be 0. This will be minus 2. This will be 0. Then 2 times of row 3 minus 2 times of row 1. So this will get 0. Then 1. Then 0, minus 1. Okay. Now this is done. Now we will scale this to 1. So because we need to create a pivot. So 1, 1, 0. Now this was fine. Then 0, 1, 0. Okay. And now we need to start cleaning down this. So you add 0, 1, minus 1. So next step would be
So can you explain the third one?
what third one?
The third matrix.
Yeah, see, this is row echelon form. This is very basic. I think you should know that. Okay. Uh, okay, fine. So then 0. Now I need to start cleaning down this pivot. So I will try to convert this to 0. So what will it be? It will be 0 and minus 1. Now I need a 1 here. This is minus 1. So again, so 1, 1, 0. Then we will get 0, 1, 0 and 0, 0, 1. Okay, so I am just writing the row operation. You can do it for yourself. Okay, so row 3 minus 2 times of row 1. This was your first row operation. This was your second row operation. The third row operation was R2 1 by minus 2 R2. Okay, then yeah, then we had row 3 minus row 2, and then we had finally row 3 as 1 minus 1 times of row 3. Okay, so yeah, so now you can see you just need to know how to calculate the free variables. So can you tell me how many pivots are there?
3.
3, right?
3.
3.
Okay, now yeah, number of pivots is equals to 3. Okay, now what is the rank? Is rank same as number of pivots?
Yes.
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 Okay, so number of pivots is equals to 3, that is rank. So we have answered, I think, first question. So first question, so rank of your linear transformation is 3. Okay, now what is nullity?
0.
0.
0.
Nullity or number of free variables is equals to 0. So we have answered second question.
Sir, can you tell the definition of pivot? What is pivot?
Okay, so pivot is the first non-zero element in a row given that your matrix is in row echelon form. So first non-zero element here is 1. Okay, first non-zero element is here is 1 in this row, and first non-zero element here is 1 in this row. Okay, is this
Is
clear?
that, sir, but rank is the number of independent columns, right, sir?
Yeah, all those are equivalent. Okay, so number of pivots basically represents the I mean dependent variables. Okay, can you repeat what you said?
So it's number of independent columns. Rank is number of independent columns.
Yeah, that is one interpretation. So yeah,
Or
exactly.
non-zero rows are said to be rank.
Yeah, non-zero rows are your independent rows. Okay, and non-zero columns. Okay, sorry, not columns. The columns with pivots are your independent columns. Okay, because there could be there could be a case where your row echelon form looks like this: 1 1 0 2 0 0 0 0 0. Now this is not a non-zero column, but it is missing its pivot. So this was actually a dependent column. Okay. So in case of columns, you need to have a pivot. Okay, and for it to be an independent column, and for rows, it needs to be a non-zero row. Clear? Clear?
Okay, sir.
Now, yeah, nullity we have answered. Now number of free independent variable, all those terms are same. So we have answered this. Now, okay. Now on to. So what you have to do to check onto. To check onto. If okay, just wait 1 minute. Okay, so to check onto, if number, or you can say if number of if rank is equals to dimension of codomain, then it is onto. So tell me, what is the rank?
3.
3.
3.
Now what is dimension of codomain?
3.
3.
What is codomain? This R3. It
R3.
is it is 3. So it onto?
Yes.
Yeah, so it is onto. Okay, so Just you have to check this. If rank is equal to dimension of codomain, then it will be onto. Now,
So, what is the dimension of codomain?
sorry.
May I know what is the dimension of codomain?
Yeah, I cannot hear you. There's a lot of background noise from your end.
So, may I know what is the dimension of codomain?
So see, dimension of your codomain. In case it is given to be a simple geometric space like Rn, then this Rn is the dimension of that geometric space. But if it is some like suppose if it is some custom, not custom, if it is some arbitrary vector space, then you would need to know information about these. Okay, you will have to calculate dimension of this codomain. Okay, generally when such a codomain is given, just see the number given here, which is your n Rn on the top of that is your superscript. Okay, so
Or
here you can
maybe,
see it is 3.
or
What?
maybe is it the number of variables?
Number of variables, what? Like,
Is it the
see,
dimension of codomain?
no, that is when we are talking with respect to row echelon form. Right now I'm saying that this is the codomain. If you know, you can see its
Okay.
dimension. So this 3 is the dimension of the codomain. So it is equal here, so it is on to. So okay, so here
Okay,
it is
sir.
on. Okay, so it is on to.
Sir, that is nullity.
Sorry.
What is the definition of nullity?
Okay, please mute yourself, whoever is this. Just wait 1 second. Yeah, go on. Someone was asking something, right? Someone was asking something, right? Hello, am I audible or
Sir,
not?
what is
Yeah.
nullity?
Uh, can you repeat what you said?
Sir, what is nullity?
What is?
Nullity or
Uh,
null.
I- okay, see, nullity is number of free variables. So basically, you have to see which how many columns are missing the pivot. So here no column was missing pivot since all 3 columns had pivots. So that's why nullity is 0. So if some of the column, if any one of the column or 2 of the column were missing pivots, then we would have said that nullity is 2.
So it is rank plus nullity is equal to dimension of the matrix, right?
Yeah, no, rank plus nullity is equals to number of columns in the matrix
SNN.
is equals to n. Okay, and you should know that rank of a matrix is always less than equal to minimum of m comma n, where m and n is this, that is m cross n is the order of the matrix. So rank, so you will extensively use these two. Okay, we will see this in examples. Okay, these two to answer lots of questions. Okay, so to check 1 1, okay, if nullity is equals to 0, then it is 1 1. Clear? Now tell me, is the nullity 0 here?
Yes,
Yes.
sir.
Yes.
Yes.
Yes, sir.
Yes.
Okay,
If it's not
so
0, then what it will be, sir?
then it is not 1 1. So this alternate definition which was given in your lectures is the same thing, that is this statement says that nullity should be 0 for a linear transformation to be 1 1. Okay, are you getting this? Okay, so you just have to check whether
Yes.
nullity is 0 or not. Now okay, for those who want to understand why, okay, those who want to understand why this rank needs to be equal to dimension of codomain. Okay, so see, you know that okay, for before that let's see one more thing. So okay, Is it an isomorphism?
Yes.
Yes, sir.
Yeah, it is both isomorphism. Oh, sorry, it
Because
is both one.
R3 is the domain and tends to R is a codomain.
Yeah. So see, you can see that it is both 1, 1 and on 2. So you can say that it is an isomorphism.
Yes.
So can you show the previous page?
Just wait 1 second. Which one? This?
No, sir. Previous page.
This?
No. That starting definition.
This?
Yes, sir. One second.
So see, what it is saying is, you know that f can be represented as ax, right? F can be represented as ax, you know that. Now it is saying that if f of b is equal to 0 implies that b is equal to 0. Okay, that is ax is equal to 0 should imply that x should only be equal to the 0 vector. That is ax is equal to 0 should only have trivial solution. Now when does it have trivial solution? When does it have trivial solution?
When AX is
When
0, like all.
Yeah, when
nullity
there is
0.
no, yeah, when there is no free variable, if you remember.
Yes, sir.
Okay, so that's why this is equivalent to saying that nullity should be 0. Okay.
One second, tell what is
Excuse
the
me, sir.
condition for onto
Yeah.
in that example.
Yeah. Okay, first someone said excuse me, right? So
Yeah, sir, can we start solving the PYQs? This is the theory that's being
Yes, sir.
explained.
I mean, we are really sorry
Yeah.
to interrupt,
Yeah.
but all these things have already been discussed in the
Okay,
previous sessions,
fine,
and we
fine.
were waiting for the session, sir.
Okay,
So since
okay,
6
fine,
o'clock
fine,
we're
fine.
waiting.
Okay, so this is an isomorphism. Okay, then you know range. Just 1 minute, I will tell you. Okay, fine. Sorry for that. So range, what would be range? Range would be, you will see which columns have pivot. Okay, so span of those columns will be range. Okay, then kernel null space you can calculate it, right? Okay, so let's start the PYQs. Okay, I think
Sir, just to finish this, at least this range and kernel, and we can do it. Already we are taking notes.
okay. I will explain it afterwards. Okay, I will explain it for sure. Okay, only 2 parts are left, but let's start. Okay, so this is your first question. So fine. Okay, so
So you
let
can
A.
able to explain that by solving the PYQ, sir.
What? Sorry.
You can able to explain that by solving PYQ questions.
Yeah, exactly. So okay, so let A be a 3 cross 2 non-zero real matrix. Okay, so it is saying that A is a 3 cross 2 matrix. Now the maximum value of nullity A is, so one keyword here to notice is that it is a non-zero real matrix. So this will play a pivotal role. Okay, so the two identities which we'll be using is rank of, okay, please mute yourself, whoever this is. Can you please mute yourself? Okay. Oh, okay. So rank of A, you know, is less than minimum of 3 cross 3 comma 2. So that means in this case rank will be less than equal to 2. Okay. So rank will vary from 0, 1 and 2. Now it is saying that, now the other which we'll be using is rank plus nullity is equals to 2. Okay. So these two we'll be using. So I have written here rank is less than 2, so 0, 1, 2 are possible values which it can take. So corresponding to that we have calculated the nullity. Okay, so for 0, rank as 0 it will be 2, for rank as 1 it will be 1, for rank as 2 it will be 0. Now nullity will be max when rank is least. Okay, because these are two positive quantities. Okay, so when one will take maximum value, the other will take the lowest value, and it is asking maximum value of nullity A is. Okay, so maximum value of nullity will be when rank is least, right? Yes or no?
True, sir.
Yeah.
The
So
rank plus nullity should be equal to number of variables in the matrix, but it is written that it is two. So why two? So that
your voice is not clear. Okay, so just
saying
wait one
that
second. Let me explain this. Okay, so nullity will be max when rank is least. Now, what is the least value of rank? Is it 0? Okay,
Yes.
so here we can see it is 0, but it is given that it is a non-zero
No, sir,
real
it's
matrix.
not possible.
Yeah. Okay, so for rank is equals to 1, so the next least value of rank is 1, so corresponding to that the nullity will be 1. So this will be the max value which it can take. Is this clear? Is this clear?
Yes, sir,
Sir.
yes.
Okay, see.
So here the maximum value of the nullity will be 1, na?
Yeah, because see it is given non-zero real matrix, so
Yes,
when
sir.
would
If
have
it
been the
will
rank?
be 0, then it can be good.
Yeah, since it is a non-zero real matrix, it has to have rank of at least greater than 1. So when rank is 1, we will have the maximum value of nullity, that is 1. So that's why its answer is 1. Is this clear?
Yes,
Yes,
sir.
sir.
Now, second question. Yeah, so this question, Anamalila Subhashish. Okay, so pool together money. The sum is distributed across 3 accounts, A1, A2, and A3 as x plus y, z minus 2y, 2y minus z. Okay, so basically they have given you the linear transformation. Okay, this is the linear transformation which has been given to you. Now, which of the following vector spaces consist of vectors which could denote the amount of money deposited by this in particular, such that in that month amount deposited is 0 in each account. Okay, that is, it is saying that uh, where did it go? Yeah, in it is asking you to find the null space. Okay, just read this question. Which of the following vector spaces consist of vectors which could denote, okay, vectors which could denote the amount of money deposited by Anamika, Subhashish, and Shreya in particular month is 0. Okay, so you have to find t of x such that it is equal to 0. So all such vectors for which transformation maps all those vectors to 0. So basically they are asking you to find the null space. Is this clear? Is this clear? So
Yes.
yeah, this is your linear transformation. Now we have to find the null space. Okay, but first we have to find the matrix corresponding to this linear transformation. So what we did, we took the standard basis vector set for the input codomain, which is your R3. So, okay, then we applied the linear transformation and found its images. So these are the images. Okay, is this clear? And we place them in a matrix. Now we have got the matrix corresponding to this linear transformation. Now we can easily find its nullity, null space. So we start converting it to its REF. Okay, so do you want me to explain each of these steps because I have already completed it, or do you want me to just explain this?
No, sir, we
Sir,
understood.
Okay.
after
just
this
explain
REF, can you please go
this.
through, say, till now we have seen the REF, so we
Okay.
can proceed
Okay.
to find
So
the null
yeah.
space, right?
So see, we will convert this matrix to its REF. So this will be the REF form. Now you can see that this column is missing the pivot, right? This is missing pivot. So x3 is your free variable. So I have assigned a value of t1, okay, t1 to it, which is a parameter. Now dependent variable x1 and x2 have been expressed in terms of x3. So x2 has been expressed as 1 by 2 of t1 and oh, please mute yourself, otherwise I would have to remove you from the meet. Okay, now x1 I have expressed in terms of t1. So this is your x1. Now express the null space, which is your minus 1.5 t1, because your x1 is 1 minus 1.5 t1. Then x2 is 1 by 2 t1, so 0.5 t1, and x3 was t1. So this is your null space. Okay. Now null space can be expressed as this or this span of this. So you can see the answers. Okay. Now the thing is this is a basis vector, but you can see that none of the answer matches, right? None of the answer matches, none of the option matches here. Okay,
Sir, can you
because
zoom in?
none of the option matches here, but you can see that if you scale this basis vector, because basis vector is never unique for this null space, so you can just scale this vector. So if I scale it by 2, so minus 3, it would become minus 3, 1 and 2. So just now see the options. So it would be minus 3, 1, this one. Is this clear? Is this your null space?
Yes, sir.
Yes, sir.
Okay, so this is your null space. Now what is the nullity? Nullity, again go back to the row echelon form.
1.
Nullity is 1.
Nullity
Okay.
is 1.
Yeah. So nullity is 1. So
Sir,
nullity
can you
is
please
1.
tell from null space how we can say nullity is equal to 1?
So you can see it here also. There is only one vector present here. So it will be 1. And other way to see it here is that this column is missing pivot and there is only one such column. So nullity is 1. Okay.
What do you mean by missing pivot?
So see, there is no this column is missing pivot. That is the first non-zero element is missing here. All the elements are 0. Okay, in this column. So this is
So you
missing
can
pivot.
move on to next question, sir.
Yeah. Okay. So what is the rank? So nullity is 1. What is rank? Rank is 2, right? That is those columns which have pivots. Okay. So they are 2. Now, which of the following option is true? Now tell me, just use the logic which I told you. Okay. So tell me, nullity is 1. So is it 1, 1?
No, sir.
It is not 1, 1. Then what is the rank? It is 2. Now tell me, is it on 2? What is the rank of the codomain?
It's a 3.
3.
No, sir.
No.
Okay. So it is neither 1, 1 nor on 2. Is this clear?
Yes, sir.
Okay.
Yes,
Fine.
sir.
Yeah. So let's move on to the next question.
So can you please explain the three formulas relating to nullity, rank, and number of two variables?
See, I'm not able to understand your answer question properly. So please type it in the chat box if possible. Okay. So now, question third. Which of the following option is are true? If A is a non-zero matrix of order 4 cross 3 and rank of A is 3, then rows of A are linearly independent. Just wait 1 minute. I have to. Okay. Okay, so please try to mute yourself and only unmute if you have a doubt. Okay, because otherwise the background noise becomes too much. Okay, fine. So A is a non-zero matrix of 4 cross 3. So I have written a matrix of 4 cross 3. Okay, I have taken a random example 4 cross 3. So this is a 4 cross 3 matrix and rank of A is 3. So that is all pivots are present in all three of columns. Then rows of A are independent, linearly independent. Now tell me, are they linearly independent? Because see, this fourth row is entire 0 row. So you know when a 0 row is present, it is not linearly independent. It was dependent. That's why it got converted to 0 row, right? Yes or no?
Yes, sir.
Okay. Now, fine. So first option is wrong. Now, if A is a non-zero matrix of order 4 cross 3 and rank of A is 3, then columns of A are linearly independent. So same example works for that, because this part till here it is same. Okay, so you can see that all three columns have pivot, and when columns have pivot, then we say that columns are linearly independent. So this is true, right? Is this clear?
Yes, sir.
Now third option. If A is a non-zero matrix of order m into m plus 1, m is greater than 1, then maximum possible nullity of, okay, again, maximum possible nullity. So nullity will be maximum when rank is, tell me,
Minimum.
when rank is
0.
yeah, when rank
Rank
is
is
minimum.
1. 0.
Yeah. Okay, we will see what is the answer. Okay, so see, this is your matrix. Again, please mute yourself. Mute yourself. Okay, so A is a m cross m plus 1 matrix, and m starts from 2, 3. Okay, it has been given that it is greater than 1. Then maximum possible nullity of A is, we have to find that. So we will use this identity, that is rank is less than minimum of m comma m plus 1. So rank will be less than equal to m. Okay, fine. Now it is saying that A is a non-zero matrix. So again, rank could not be 0. That's why I have cancelled 0. So all these are the possible. Okay, please mute yourself again. I'm requesting. Okay, fine. Okay, so yeah, so we have eliminated 0 as a plausible candidate. Okay, so these are left. I have given the reason also. So now I will use my second result, which is rank plus nullity is equals to m plus 1, right? Because m plus 1 is your number of columns. Okay, so now I've written 1, 2, 3, all the possible values of rank. Then I've calculated the corresponding value of nullity. So rank nullity will be maximum when rank is least. Okay, so how, so from this I substituted 1 here, and nullity came out to be m. Is this clear? Is this clear? Any doubt here? Any doubt here?
No, sir.
Okay, now so this option is correct. Now D. If A is a non-zero matrix of order 4 cross 5 and rank of A is 3, then dimension of solution space to the homogeneous system AX is equals to 0 is 2. So this whole thing is nothing but asking you the nullity. That
Yes, it is right.
nullity is 2. Okay, so if rank is 3, then rank plus nullity is equals to 5. So it will be 2, right? Tell me.
Yes, sir.
Okay, so I have written it here. Rank plus nullity is equals to 5. Rank is 3. Nullity will be 2. I hope everyone is understanding, right?
Yes, sir.
Sir,
Option
please
B.
repeat last
Once more
point.
explain.
Sorry?
Sir, please explain the option number B. Option B.
Option D.
The option D also.
So see, they have given you order of the matrix 4 cross 5.
No, sir. Option B. Option B.
Option B. Okay. So see, rank of A is 3. This means that all the columns have pivots. Okay. When all columns have pivots, so all those are linearly independent. Is this clear? If any of the column was missing a pivot, then we would have said that columns of A are not linearly independent. But here you can see that none of them is missing a pivot. Okay. So I will move on to next question now.
Sir,
Sir,
you will
please
share
repeat
this
the D point.
solution PDF, right?
Oh, yeah, you will get the solution PDF.
Sir, please repeat D point.
What? Sorry.
D point.
So see, rank was given as 3. So you will use this rank plus nullity is equals to 5. That is the number of columns present in the matrix. So you will substitute 3 here. plus nullity, and you will calculate it. Nullity will become out to be 2. Okay. So
Okay, sir.
So just one
the
last doubt.
see the dimension of solution space of the homogeneous system. So this is basically asking you dimension of the null space, which is equal to the nullity, right? Is this clear?
Yes, sir.
Fine. Okay. Then this question, fourth question. Okay. So now, yeah. So this is a linear transformation which deals with a arbitrary vector space of matrices. Okay. So now let's see. So now you would have to first of all determine sub dimension of this codomain. How we do that? We try to express this general element as a summation of such matrices. Okay. So first of all, they have given you the linear transformation, which is this. Okay. So I've written it down. I've written the codomain vector space. Okay. Just wait 1 minute. Just wait 1 minute. Okay. Okay. Sorry for the interruption. I had to move to a different place. I'll start just. Okay. So am I audible?
Yes.
Just zoom in a little bit.
Yes.
We can't
Sorry.
see. If you can zoom in a little bit.
Okay. Okay. Fine. Okay. Is it visible now?
Yes.
So now, yeah. So where was I? Okay. So I have written the linear transformation. Now to answer, we have to find again. We have to see to answer anything. We have to find the corresponding matrix. Okay, corresponding to this linear transformation. Okay. So how we will do that? So first of all, you will find pick the standard basis vectors for this code for this domain, which is R3. So I have picked up those. Okay, so these are your standard basis vector. Now, okay, now basis again we have to find basis set for your codomain also. So your codomain is this set. Okay, so now what I will do, you have to find basis set for this codomain. So I will express this general element as this. So A, I can write this general element as A1100 plus B0011. So now how did I do that? So see, you will first of all list all the variables which you can see in this general element. So you can see two variables, right? Yes or no?
Yes, sir.
Yes, sir.
Okay. So one more thing, if some condition was given here, suppose some condition was there, okay, so involving the variable, suppose if there was c is equals to C plus A plus B is equals to 5, uh, you know, 0. Suppose such condition was given and there was a C element here. Okay, suppose there was C element here. Then what you will do, you will use this you will C is equals to minus A minus B. Okay, you will transfer all the elements, all the on the LHS to RHS except one variable. Then you will substitute minus A minus B here. Okay, and then you will operate on this general element. Right now there is no such condition given here, so we will directly jump on to the general element. So this is A B B. So now wherever A is given, so I wrote A. Then wherever is A is given, I will write 1 1, and there here there is no A. So if there was a plus A, then I would have written 1. Okay, but there is no plus A, so I have written 0. So 0 0 plus. Now for similarly we will do it for B. So B, here there is no B 1, there is B, so 1 1. Okay, so that's how we write that. Now these two are your
So,
bases. Yeah.
so from where we got this basis set for V, A, B, B? I could not understand.
Okay, so I will just give you. So see, suppose this was given. Suppose a set is given, any such a set is given, A B C D. Okay, A comma B comma C comma D belongs to real number, and a condition is given, D is equals to 5A, sorry, D plus 5A minus 2B plus C is equals to 0. Such condition is given. Okay, so this is a set is given. So to find the, to find the basis set for this set, how do we do that? First of all, see, there is a condition given here. So what you will do, you will pick any one variable. So I picked the D, and now I will express it in terms of the other variable. So this would be minus 5A plus 2B minus C. Now I will substitute it here. So I am reducing one of the variables in the general element. So A, B, C. Now in place of D, I would substitute this. So minus 5A plus 2B minus C. So now I've got my general element. Now what I will do, I will list all the variables I can see. A, B, C, right? I can see 3 variables. Yes or no?
Yes.
Yes.
A, B, C. Now what I will do, I will pick the first element, A. Okay. Now I will see in this general vector where all A is present. So A is present here. A is present here. So in all those places, I will place value of A as 1 and rest all of them as 0. So tell me what will be the matrix here. So in place of A, I will place 1 1. What will be here?
0 minus 5.
0. C as 0. Then I will place here 1 and rest all 0. So it would be minus 5, right?
Yes, sir.
Now I will do it for B plus B. Now see, I will place B as 1 and rest all variables as 0. So 0, 1, 0, 2 plus.
So basically linear combination, no sir?
Yeah, exactly. Okay. So now C, for C, you will do 0, 0, 1 and minus 1.
Minus 1.
So now these matrices which are present in front of these coefficients A, B and C are your basis set. Okay. So that's what I was doing here. Is this clear?
So if suppose if it is a 3 by 3 matrix.
Sorry?
Suppose if it is a 3 by 3.
Yeah, just you have to repeat the same steps. Okay. It can be 100 cross 100 matrix also.
So only for one element we have to write it as a combination of the remaining.
Yeah. You could have taken A, you could have expressed A in terms of D, B and C also. Then you would have to replace A here, whatever you got here. Okay.
No. What I am asking is the number of elements present. Now here it is 4. It may be 4 by 3 matrix also, or 3 by 5 matrix.
Yeah, it could be any matrix.
In any matrix. So we have to represent only one element in combination of the others. Then we can get the basis.
Yeah. If two such conditions are given, then we will see it. Okay. So yeah, but now this much works. Okay. Okay, so I will not remove this. Okay. You can see it. I will. Okay. Now see, what I did was I expressed this general element as linear combination of basis vectors. So these I found my basis vectors. Now what I will do? Now these were my basis vector for for domain, and these are my basis vector for codomain. Now number of basis vector tells you what is the dimension of the codomain. So what is the dimension of the codomain? Is it 2?
2, right.
Okay, so it is 2. Now what I will do, I will use this linear transformation which is given to us, which is this. Okay, so the method remains same. So I will find the images. So for first basis vector of domain, I will find the image which is this 1 1 1. Then for second,
So first
and
you're
then what?
keeping x as 1 and second you're keeping y as 1 and next you're keeping z as 1, right, sir?
Sorry, where?
First you're keeping
He's
x as
saying about
1.
the basis of the domain.
See, these are your standard basis vector, right? 1 0 0, 0 1 0, and 0 0 1. So I'm finding the images of those according to this linear transformation, which is this. X5, x plus y, x plus y, x plus y plus z, x plus y plus z. So this is your linear transformation which is given in your question. Are you getting this?
Okay.
So
Yes, sir.
these are the images. Now I am expressing these images as linear combination of the basis vectors for the codomain. So see, what we found for the codomain were these basis vectors 1 1 0 0 0 0 1 1. So I have expressed them here. So see, all these are same. So 1 0 0 1 1 0 0 1 1 0, and okay. So these are, I have expressed this as linear combination of those. So 1 1, again this is from week 6, 1 1 1 1. Now I have placed these coefficients. So 1 1 as one of the row. So this row as this, then 1 1 as this row, sorry, column, and then 0 1 as this column. So this is your matrix corresponding to this linear transformation. Now you can tell everything. You can see that there are how many pivots present? Only 2 pivots present. This column is missing a pivot. So nullity is 1 because one of the column is missing pivot. So this is not 1 1, right? Yes or no?
Yes. Yes.
Now what is the rank? Rank is 2. So which is, now tell me, is it equal to, rank is 2. Now is it equal to the dimension of the codomain?
Yes.
So is it one, is it on 2?
Yes.
Yes. Okay, so it is on 2. So what will be the answer? So it is not 1 1 but on 2. So it is not, yeah, it is on 2 but not 1 1. Is this clear?
Yes.
Yes, sir.
Sir, small help, sir. So
Yeah.
can you go to the previous page? So little bit fast, because if we can understand one question properly, we don't need to rush anything. So to be honestly speaking, we are all working profession and we have this only
Yeah,
one
yeah, yeah.
session.
Fine, 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 fine.
So
Go on.
please, no. So
Yeah,
just
yeah.
we have calculated the pre-image and we are converting to the codomain vector space with the pre-image. So there.
Wait. Are you talking about this fourth question?
No, no. Yes, sir, yes, sir. In the fourth question only. So
Okay.
till we are calculating the basis vector. After that, we are transposing the our standard basis to this one, and we are trying to match it to the basis vector, right? So in the third one, so
Are
yeah,
you
so,
talking about this step?
yeah, third one. That is clear, sir. See, yes,
Okay.
yes. Can you please explain one, at least one, only one mapping?
Okay.
The third
So
one.
the third one. So see, T001 gave you this map. This matrix came from utilizing this transformation which has given to us, which is this.
Yes, sir. Yes, sir.
This one. Now I will get an output matrix according to this transformation. So I got this. Now I will express this output matrix as linear combination of the basis vector which we found for the codomain. So what were the basis vector which we found for the codomain? These were the basis vector, right?
Yes, sir.
So I express this output. See, for each I am expressing the output as linear combination of those basis vector which we found for the codomain. So they see these are same. If you see this row, entire row, it is same, and this column is also same. Okay, so I am expressing those. So see 0 0 1 1 can be achieved as 0 times of 1 1 0 0 plus 1 times of 0 0 1 1. Okay, so I got these coefficients. So now these coefficients are important to me. So these coefficient I will these two I will place as column. So these are 1 1. So this one is this one and this one, and this one and this one is this one and this one. This 0 and this one is this 0 and this one. So I place them as column. So I've got my matrix corresponding to this linear transformation. Once I get the matrix, everything becomes easy. So I will calculate the nullity. Okay, so one more thing. First, I will need to convert it to REF, right? Then I will see, check the nullity and rank. So nullity is coming out to be 1 because this column is missing a pivot. And rank is coming out to be 2 because these two columns have pivots. So it is on 2. Clear? Now, what was the dimension of codomain? We found it here. We expressed this general element. So there were two such matrices. So 2 is the dimension of the codomain. Are you getting this?
Yes, sir. Yes, sir.
Fine. Yeah. Then, okay. Now, fifth question.
Sir, can you zoom in, please? It's very small.
Okay. Okay, fine. Okay. Is this clear?
Yes, thank you.
Now, if A is a 2 cross 3 matrix of rank 1, what is the nullity of AA transpose? So first of all, just write a matrix A, 2 cross 3, fine. 2 cross 3, that is, it will has 2 rows and 3 columns. Now its rank is given to us as 1. So what I can do is, I know that rank is 1. So you know that row rank will be 1 because rank is the same for row rank as well as column rank, right? Column space rank. So what I did is I wrote this general A matrix as 1AB and the second row as 0 because I know that rank is 1. So the other row must be a 0 row. Yes or no?
Yes, sir.
Okay, so I wrote it. Then I wrote its transpose, A transpose. Then I calculated its A transpose. So if you see that, it is coming out to be 1A square plus B square 0 0 0. Now what is the nullity? Nullity is nullity. So see, these are positive values. So this will be a non-zero value. Okay. So only this column is missing a pivot. So nullity is 1. Is this clear?
Yes.
Okay. So what is nullity of AA transpose? It is 1. Okay. Now, sixth question. Which of the following options are true? There exists. Okay. So you need to check whether there exists such a linear transformation, which is onto from R3 to R2. Okay. We will see that. Okay. So yeah. So it is saying that there exists a linear transformation from R3 to R2, which is onto. Okay, so when a linear transformation is from R3 to R2, you know that the matrix corresponding to that linear transformation will be of order 2 cross 3. That is, 2 you will pick from your codomain and 3 from your domain. So this will be the order of the matrix. First tell me, is this part clear?
Can you repeat this again?
What? Sorry?
Can you repeat this again?
So see, these from your input domain is R3, that is you are feeding input vectors from your R3 space and you are getting output vectors in R2 space. So just simple matrix multiplication will tell you that, see, this X vector is your input vector, which is being multiplied with A matrix, right? Corresponding to this linear transformation. Now this is 3 cross 1 because this belongs to R3, right? So what should be the order of A? First of all, it should have a 3 here only then it will be multiplied with x, right? Yes or no?
Yes, sir.
Yes or no? Now, what should be the vector dimension? Sorry, what should be the order of the vector? Since you are getting outputs in R2, should it be 2 cross 1? So should it be 2 here? So is the order of A 2 cross 3? Tell me.
Yes.
Okay, so that's why it is 2 cross 3. Now, it is saying that there exists an onto linear transformation from R3 to R2. So for onto, what was the condition? Tell me. For onto, what was the condition? Rank should be equal to
Rank of the R2 domain means rank should be equal to the codomain. So
rank should be equal to see here, what is the dimension of the codomain? Is it 2?
Yes.
Okay, is it 2? So now does there exist, if I suppose I have drawn these boxes, so now I'm going to fill these. Okay, so suppose this was my matrix. Now tell me, what is the rank here?
It's a 2.
Okay, so there does exist such matrix, yes or no? This is a
Yes,
valid this is a valid matrix, right? Valid transformation. So it exists, right? So it is onto. So there exists such an onto matrix. Is this clear? Is this clear?
Yes, sir.
Yes, sir.
Any doubt here? See, they are asking you to find whether there exists. So if you are able to come up with an example, which is an onto linear transformation of order 2 cross 3, then you can say that yes, there exists. No problem in that. Okay, now there does not exist a 1-1 linear transformation from R3 to R. Okay. Now
it's not. It is true, sir. No, that does not exist. One.
okay, we will see that. Okay, so see, T is from R3 to R. Now tell me what will be the matrix order of the linear transformation?
1:3.
1 into 3. So pick 1 from here, 3 from here. So this will be 1 into 3. Now you know that rank will be less than equal to minimum of 1, 3. Right? So it would be rank will be less than equal to 1. Okay. So rank could be 0 or 1. Now, what is the nullity? Nullity, we have to find it. Okay, so rank plus nullity is equals to 3. So when rank is 0, so you know that for this matrix rank can only take 0 or 1. So I have calculated the corresponding nullity for 0 and corresponding nullity for 1. So nullity is 3 and nullity is 2. Now in any case, is the nullity 0? Is the nullity 0 in any case?
No, sir.
No, sir.
No.
I've written it here, nullity cannot be 0 in any case for this linear transformation. So there does not exist a transformation from R3 to R such that it is 1, 1. Okay, is this clear? Is this clear?
Yes, sir.
Okay, fine. So this is wrong. Now there exists a linear transformation from R3 to R2 such that rank is equals to nullity. Again, let's see it. So your transformation is from R3 to R2. So what will be the order of the matrix corresponding to this linear transformation? 2 cross 3. Yes or no? Right? Let me check. Okay. Yeah, it would be 2 cross 3, right?
Yes, sir.
So yeah, it would be 2 cross 3. Now, rank would be less than equal to minimum of 2 cross 3, that is 2, right? So I've written this here. Now rank plus nullity, you know, is equals to 3. That is the number of columns. Now they are saying that rank is equals to nullity. Does there exist such matrix? So what I will do, so such that rank is equals to nullity. So I took rank as k and nullity as k because they are saying that they are equal. So I substituted k here. So k plus k is equals to 3. Now 2k is equals to 3, k is equals to 3. Right? Now tell me, can rank ever be, fraction
No,
or
sir.
nullity? No.
No.
So there does not exist such linear transformation. Is this clear?
Yes, sir.
Okay. Now D option. Okay. Now D option. So this is wrong. Now D option. There does not exist a linear transformation such that rank is equals to nullity from R2 to R3. Okay. So first you will write the, okay, from R2 to R3. So from R2 to R3. So what will be the order of the matrix corresponding to this linear transformation?
3 cross 2.
3 cross 2. Okay. 3 cross 2. Now rank plus nullity is equals to 2 number of columns. So they are saying that there does not exist such matrix. So we will check whether there exists or not. So what I will do, I will take rank and nullity as k. So k plus k is equals to 2. So k is equals to 1, which is a valid answer. And you can see I have also written an example for that. So here you can see that this is a 3 cross 2 matrix. What is its rank? Its rank is 1 because there is one pivot. Okay. And its nullity is also 1 as this column is missing a pivot. Okay. So there does exist such matrix. So this option is right or wrong? Tell me.
Right.
No, no.
No, no,
Is
wrong.
it? Yeah, it is wrong because there does exist such matrix, right? Is this clear? Is
Yes,
this
sir.
clear?
Yes, sir.
Okay, are you understanding?
Sir, can you explain the B option once again?
D option?
B.
So see,
AB.
when I was explaining, you should have pointed out at that point of time also, only, right? So A option, A option, do you say?
No, no, B. Just B.
B option. So it
Yes.
says that does not exist a 1-1 linear transformation from R3 to R. So let's see that. So from R3 to R. So what will be the, first of all, tell me what will be the order of the matrix corresponding to this linear transformation? It would be 1 cross 3. That is
Yes.
a row vector. Now you know that rank is always less than equal to minimum of 1 cross 3. So that is rank is less than equal to 1. So rank could be take 0 or 1. Now corresponding to that, we will calculate the nullity. So for rank as 0, nullity will be 3. For rank as 1, nullity will be equal to 2. So what we are actually here trying is that we are trying to find whether in any case nullity could be 0. But you can see that rank can, nullity can never be 0 in any case for this matrix. Okay, is this clear?
Yeah.
Okay, so that's why if nullity cannot be 0, then it is not a 1-1. Okay, so 1-1 was a keyword here. Here it was a non-2. Okay, is this clear?
Yes.
So no such 1-1 transformation exists. Okay. Okay. Now this, fine. Question 7. So let V1 denote the vector space of solution of Ax is equals to 0. So basically this is nothing but null space of A. Fine. Vector space of solution of, the solution set to Ax is equals to 0 is null space of the A matrix. Yes or no?
Yes, sir.
Now, okay, let V2 denote the vector space of solution of the system By is equals to 0. So again, the solution set to By is equals to 0 is nothing but the null space of B matrix. Yes or no? Is it null space of B matrix? This vector space of solution of system By is equals to 0? Tell me. So,
Yes,
okay,
sir.
so yeah, so these are your V1 and V2. Now, this is hinting at that you need to find V1 and V2, that is for sure. Okay. And yeah, so there are three questions for this. So what is the nullity of A? What is rank of B? Which of the following forms basis for V1? Okay, so V1 is nothing but your null space. Null space of A. Null space of A, so you can find its basis also. Okay. Then fourth question says define a linear transformation. We will see that. Okay. First, let's do first question. So A was your this matrix. Now we start its conversion to row echelon form. Okay. So we start with this element, we convert it to 1, then we start cleaning down this element. Okay. Then we move on to this element, we convert it to 1. Okay, we converted it to 1, then we start cleaning down. Then we move on to this element, but here there is no non-zero element, so we will stop here. So we have achieved our row echelon form. Now you can see from here only that nullity of A is 1 because this column is missing pivot. Yes or no?
Yes.
Okay, this column is missing pivot, so nullity of A is equals to 1. So I've got one of my answers, so this is 1. Now what is rank of B? Okay, so rank of B, so again you have to convert B to its row echelon form. After conversion, this is your row echelon form of B. So what is the rank of B? It is the number of columns with pivots. Okay, or just simply count the pivots. It is 2. So what is the rank of B? It is 2. Is this clear? Tell me.
Yes, sir.
Okay. So see, if I have to solve, it would take a lot of time, right? And we would not be able to cover lots of questions. Okay. So yeah. So rank of B is 2. So see, if you have any, at any point of time, you have any conceptual question, you can ask. Okay, so rank of B is 2. Now, which of the following forms a basis for V1? So, yeah, basis for V1, sorry. V1 is null space of A. So, you would have to operate on A matrix. So, we already have the row echelon form available to us. So, you see that x3 is your free variable. So, I assigned a parameter t1 to x3. Then I rewrote the system, these two equations. So I expressed x2. So see 1 x2 plus 4 by 3 x3 is equals to 0. So x2 would be equal to minus 4 by 3 x2 x3. So x3 is t1. So I have substituted t1. So minus 4 by 3 t1. Now same for x1. x1 plus 0.5 x2 plus 2 x3 is equals to 0. Then I transfer all the other variables to the RHS. So this will be minus 2 t1 plus 2 by 3 t1. So this will be minus 4 by 3 t1. Is this clear? So now
Yes.
I write the null space. So this is bracket t1 minus 4 by 3 t1. x2 is minus 4 by 3 t1 minus 4 by 3. Then x3 is t1. So I have written 1 here. Okay. Such that
Sir,
t
can you
belongs to real.
explain this 1 second? So null space.
Which part?
Part, sir. Like you take x3 as t1. How it is
Yes.
x2 is equal to minus?
Okay, so x3, you saw that this column is missing pivot, which is your third column. So x3 is x3 is a free variable. So I assign a parameter to it, which is t1. You could have taken any parameter. You could have assigned it p also. So x3 is t1. Now, what are my dependent variables? Okay, those who have pivot. So x1 and x2. So what I will do, I will rewrite this system. So see, x1 plus 0.5 x2. So this is from your Gaussian elimination plus 2x3 is equals to 0. Then this, so 0x1 plus 1x2 plus 4 by 3 x3 as 0. So here x2 is equals to minus 4 by 3 x3, right? So what is the value of x3? It is t1. So minus 4 by 3 t1. Is this clear? Is this
Okay,
clear?
sir. Okay.
Then similarly x1 So from first equation, 1x1 will be minus 0.5 x2 minus 0.5 x2 minus 2 x3. So I will get this. So minus 4 by 3 t1 x1. So I have written x1, x2, x3. So x1 is minus 4 by 3 d1. So I've just taken t1 common. So this is your null space. Okay. So this is your null space. Now see. Now see which of the following form basis. So basis is nothing but your this vector, which is written in front of t1. So minus 4 by 3, minus 4 by 3 and 1. Is this clear? Now can there be multiple answers to it? So basically see, this is, you need not stop here. You can see that rest of the options, if I scale this option by 3, multiply this option by 3, each of these elements by 3, so it will become minus 4, and 3. So this is also a valid option, minus 4, and 3. Okay, is this clear?
Yes.
Yes, sir.
Now we have to check other options also. So 2, let's see, 2, no, so first option is not valid. Okay, then this option 2 by 5, if I do 2 by 5, yeah, so this is also not a valid option. Okay, so these two are correct. Now fourth question, anyone any doubt still here?
Sir,
Yeah,
sir, in the last subdivision, V1 means the A matrix, right?
no, v1 means the null space. See, it is saying that vector space of solution of ax is equals to 0. Solution set of ax is equals to 0, set of ax is equals to 0 is your null space of that matrix A. Okay, so it is
Yes.
indirectly null space of A. So basically you have to find null space of A to find B1, and you have to find null space of B to find V2. Are you getting this?
Yes, sir.
Okay, so that's why we are finding null space, so that we can get some information about V2 and V1. Okay, so now fourth question. Fourth question is also related to the our question 7. So define a linear transformation T from V2 to R2. So V2 we have already found. Okay, Txyz is equals to x plus y plus z. So there are only two elements in this. What is the rank of T? So you know, whenever such linear transformation is given, you can always find the corresponding matrix and then you can answer every such question. So can you find the rank of T now? Tell me. You have V2 in your hands. You know everything about R2. So let's see how we will do that. So this is your linear transformation which has been defined for us. Fine. Now you know that V2 is this null space. V2 is this null space from here. So I have written V2 also. So I had converted V2 is null space of B. Yes or no?
Yes.
Tell me. So I have converted B to its row echelon form.
Yes.
Okay. So which is the free variable here? It is, which is the free variable?
X3.
X3. So I have assigned a parameter. I have expressed rest of the elements in terms of the free variable, which is your x3. So x1 is t1, x2 is minus 2 t1. So I've written the null space. So see, t1, x1 is t1, so t1, t1, then x2 is minus 2 t1, so minus 2 t1, then x3 is t1, so x3 is 1 here. Okay, so this is your null space. I've written it down. Now tell me, what is the basis of v2? Is it this vector?
Yes, sir.
Is it okay? So what I will do, since my domain is v2, I will find the image of the basis vector. So this is the vector I have put here. So I will find the image using this linear transformation. So this is my linear transformation image. Okay, output. So now you know that what is the codomain for this transformation? It is R2. And what is the standard basis vector for codomain? It is 1 0 and 0 1. So you can directly see if some other vector custom vector space was there. So what you will do here, you will if suppose if there was some suppose v4 and you know its bases also, it had two vectors. Okay, suppose its bases had two vectors. So what you will do, you will not stop here, you will express this as linear combination of these two vectors, and then the coefficient in front of those vectors will be placed as matrix here. Okay, so I think, yeah, okay, so this is the corresponding matrix to this linear transformation. Is this clear?
Yes, sir.
Okay, now
Sir, sorry to
yeah,
stop here, sir. Because
yeah,
as our previous examples and all, we are using a standard basis, right? So here we are, since we got the V2 as some basis, so with that one we are trying to replace that 1 minus 2 1, and we
yeah,
got this one, right? So 1 0,
so
right?
yeah,
So you mentioned previously we should mention as a standard basis 1 0 here.
so see, the thing is, these output which we get, we generally we have to express it as some, if a different vector space is given. So here you can always take standard basis vector. So see, 1 0, these coefficients, if you place them as column, it is again coming to be 1 0. That's why we can directly place it here. But if some
Yeah.
other suppose v3 was given here, instead of r2 it was v3, which had suppose these two vectors 1 2 3 4. So suppose this was the basis vector for, so suppose this is v2 to v3. Now suppose this was for v3, this was the basis vector set. Now this output would have been to be expressed as a linear combination of these two. So suppose a 1 2 plus b 3 4. You would find these and then you will place them as columns. So a b, this would have been your corresponding matrix. Are you getting this?
Yes, sir. Very good, sir. Thank you. Thank you.
Okay.
So always we need to convert the output like R2 from our
Yeah.
transformation, right?
Yeah. But see, the thing is, whenever your general geometric spaces are given, which is that is Rn, so you can always take for codomain the standard basis vector. So so here you will have your standard basis vector for Rn. So at last it will come, you will see that those coefficients when placed as columns will be the same vector. Okay, that's why I didn't express it. Is this clear? What I'm saying is, see here it is R2, so I can express it as 1 times of 1 0. So for standard basis vector for R2 is 1 0 and 0 1. So plus 0 times of 0 1, this will give me this vector. So if I take these coefficients now and place them as columns, so you can see that it is nothing but the same vector, right? 1 0, I placed
No,
it.
no,
Is this
got it,
clear?
sir. Yeah, since
Okay.
it is mentioned as a R2, we should use the standard basis. If they are
Yeah,
giving
yeah.
yes V3 or
Yeah.
some other one, we should use the basis vector, right?
Yeah, standard basis vector.
Yes.
So you wouldn't have to write these, okay? But if they mention some other basis for R2, then you would have to express those.
So they would have given the basis, then.
No. See, whenever you have to calculate a matrix, they don't give you the basis. Those questions will appear, separately, where they give you the basis for both domain and codomain, and then they ask you to find the corresponding matrix.
Okay, sir.
Okay. Okay, so yeah, one more thing, you can see that this matrix is not a according to this, what should have been the dimension of the matrix? It is 2 cross 1, right? So it is correct. Okay. Now, but you cannot express. Okay, just forget about it. Otherwise, you will get confused. Okay, so this is your matrix. Now you can see the rank and nullity. So what is the rank? Rank is less than equal to minimum of 1 cross 2. So this is 1, rank is less than equal to 1, and you can see it as 1. Okay, is this clear? And
yes, sir.
sorry, okay, so the rank is 1. Is this clear?
Yes, sir.
Okay, see, your matrix is just a column vector, so its rank is 1. Is this clear? And that to a non-zero vector. Is this clear?
Yes.
Fine. Now, which of the following are linear transformation? So these types of questions are very easy. You just have to see. Okay, tell me, is the first a linear transformation? Tell me, is first option a linear transformation?
Yes.
Why? No, it is not a linear transformation because any linear transformation,
It has a constant here.
yeah, it has a constant. So it will only be, so you must have seen a linear system of equation, right? You have x, 2x plus 3y plus 4z is equals to 5, right? So here you only have the linear equation, and here you have the constant. Okay, so only these types of expressions should appear. Okay, 2x plus 3y plus 4z, only these types of. So let's see. This is wrong. Okay, so there is a constant here, so I will point it out. Constant, so this is wrong. Now t of x y z w is equals to x plus y, so this is fine, comma z plus w, so this is fine. Okay, so this is correct.
Sir,
Yeah, yeah.
sir, do we have to verify with the axioms?
No. See, here you can directly see it. Okay. Okay, so in exam you don't have to verify. For your formal, notes, you can verify it in your notes. Okay, so this is a trick. So basically you can see, not trick but fact, that you can see that these are linear combination of variables and no constant is there, and the degree of each of these variables is 1. If it was x square plus y comma z plus w, then also it would have been wrong because this is x square. Okay, so only degree should be 1 and no constant should be there. Is this clear?
So can you
Sir,
do
if it is all are in the same degree, what will happen? So x square plus y square, comma z square plus w square, what will happen? Sir?
No. So I said that degree should always be equal to 1. So if it is x square plus y square comma z square plus w square, then also it is not a linear transformation because this degree is 2. It should only be 1 for any variable. Maximum degree should only be 1. Is this clear?
Okay.
So basically, see, I am telling you, right? You have seen a linear system of equation, right? 5x plus 2y minus 3z is equals to 10. 2x plus 4y is equals to 6. Z is equals to 5. So is this a valid linear system of equation? Yes. So only the all the inside the parentheses, only these types of expressions should be there. Are you getting this? There is no constant in addition. Okay, so only the LHS part should be there. Is this clear?
Yes, sir.
Could you explain it once?
That is basically linear combinations of variables should be there. That is cx plus y. So such an expression should be there. All degree is 1 of all variables, and there should be some coefficient. There should never be any constant here. Okay, so this is wrong. Okay, so your expression should always be like this inside the parenthesis. So this is some valid, this is a valid such expression, also this. So this is correct. Now this is also valid, this is also valid, this is also valid, this is 0. Okay, now
So if
yeah,
0 is there is a 0 vector is a valid, sir?
so 0 element, you can write it as 0x plus 0y plus 0z.
Okay.
Sir, but
Okay.
how is it in R3 again?
Sorry?
Sir, here it's shown that it's from R3 to R3, but like after the
Yeah.
transformation, it's just X and Y and then 0. It always stays in R2.
No, see, it is, see, R3 is R3. It is staying in XY plane in R3. It is not R2. It is XY plane in R3.
Okay, the plane of
Okay.
F1.
There's a difference between, see, if this Z coordinate is 0, how many coordinates are still there? There are still 3 coordinates, right? So it is still a vector in R3. R2 vector only has 2 elements. Is this clear?
Yeah.
Okay. So this is a difference. So this is a valid linear transformation. Now what about this? This
It
is
is
wrong
not
because
valid,
there are
sir.
constants. Is this clear? Clear?
If
Yes, sir.
it is 0 means it will become a plane
Sorry?
minus y minus z 0.
Yeah. So basically, see, this is this type of linear transformation. So this is your domain.
Will pass through origin.
If you apply a linear transformation on this, or if there is a vectors like this, suppose there is a vector 4, 3, 2. So after this linear transformation, it would become, I am drawing it in the same graph. So after transformation, it would become minus 3, minus 3,
Minus 2.
minus 4, 0. That is a vector in the xy plane. So minus 3, minus 4, and 0. So basically, it is this vector was mapped to this vector.
Okay.
So basically, what it will do, if there are lots of vectors here, it will just compress it on the xy plane. All the vectors will be compressed on the xy plane. Are you getting this?
Okay.
Okay. Now, okay, fine. Now, ninth question. Let T be a linear transformation from R2 to R3. Fine. S is a subset of R2. Okay, is a line passing through the origin. Which of the following are possible? T of S. Okay, so first of all, T is from R2 to R3. What will be the order of the matrix corresponding to this linear transformation?
3 by 2.
3 cross 2. Okay. Now, okay, so eighth question we have already done. Done. Okay, so completed. Now, yeah. So T of S. So basically, see, your input domain is whole of R2, but it is asking output. So see, this is your R2. Input domain is whole of R2, but it is asking you the output set, that is the image set for a particular set of inputs, which is your S. So suppose this is your line in S. So I think I have drawn it here. No? Okay, fine. So it is asking you, so this is your S. So it is asking you this is your image set. Image image set of S. Okay, this is not image, this T of S is not image set of your whole of R2. It is only for this input set. Okay, now T of S could be origin in R3. These are it is asking you whether these are possible or not. T of S could be R3. T of S could be a plane passing through origin in R3. T of S could be a line passing through origin in R3. So let's see that. So yeah, so S is a one-dimensional subspace of R2. Now matrix corresponding to T is of order 3 cross 2. So I've written a matrix of 3 cross 2 order. So it will have 2 columns only. Okay, these columns will have 3 such elements. Okay, now S is a line passing through origin. That is fine. So I have written it here. So I can express that line as this, right? T times of AB. Yes or no? So suppose the line is along AB vector.
Yeah, right.
Okay. So I can express the whole line S as T of AB, right? Scalar multiple of AB would be representing this line. Yes or no?
Yes.
Okay, so I've expressed this here. Now there are multiple cases. Because they have not defined anything regarding this linear transformation. Okay, so we have to consider each and every case. Okay, which is this. So this is a 3 cross 2 matrix. Okay, again 3 cross 2 matrix, 3 cross 2. You know that it has only 2 columns. Okay, so I have taken all the 3 cases. So what are the 3 cases? When both columns are 0 0 0. Okay, then second is one column is C1 and the second column is a linear, I mean it is dependent on the first column. Okay, then second is both columns are independent. Is this clear? So I have taken all the 3 cases. So when this is the case, all the elements from your S line will be mapped to 0 because this is a 0 matrix itself. Yes or no? Tell me. Tell me. Yes or no?
Yes, sir.
Okay, so any vector from this S line. So if you take this vector, this on being multiplied with this possible matrix will be mapped to 0. So T of S could be origin in R3. So is this a valid answer? Tell me. Is
Yes,
this a
sir.
valid? Oh, sorry, someone was saying something.
Sir, I
Hello.
told yes, sir.
Yeah, so it is right. Okay, so T of S could be origin in R3. Now T of S could be a, so see, T of S could be a line passing through origin in R3. Now, second case is this. Second and third case are these. When one of the column is dependent on the other and both columns are independent. So when one column is dependent on another, that's why I've written C k times C. That is, it is scalar multiple of C1. Okay, because two vectors are dependent when one of the vectors could be expressed as a scalar multiple of the other vector. Yes or no? Yes or no?
Yes, sir.
Okay, so now I have written this matrix. Now I am taking any general vector from the S set. So that's why I have written TA, TB, right? Now I have written the image set. So this is, see, you know that how to multiply vector multiplication, right? So this will be TA times C1 plus TB times KC1. Yes or no? Yes or no? Yes or
Yes,
no?
sir.
Now what I will do? I will take C1 common. Okay, C1 common. C1, because vector is distributed over scalar addition, right? So C1 times TA plus TBK. Now all these are constants. Okay, scalars. So I have replaced it as a different scalar. So K dash. Now tell me, is the TS image set a scalar multiple of a column? So isn't it a line? So isn't the range a line passing through origin? Tell me. Yes or no?
Yes.
Are you getting this or not?
No, sir.
No?
Sir.
No, sir, we're
Scalar
not getting it.
multiplication is getting, sir, but the range which you are referring, the final output, which I'm not able to get.
See,
Till the scalar multiplication is fine, sir, because it was division, and then it was converting to k dash c1 this part, and the final
okay,
conclusion
so
is.
okay, fine. So see, you don't need to worry. The thing is, see, A, B are constants. The only multiple is T. We are varying T, right? T gives us different vectors in your S line. Yes or no? Tell me.
Yes, sir, that is correct.
Okay, A and B are constant. Fine. Now K is also a constant because it was already decided. Okay, K is also a constant. So A, B, and K are all constant. Now T is a variable. Fine. So okay. So what I can do, I took C1 as common. Fine. Then the only I could have taken T also common out. Okay. And A plus bk. So suppose I can write it like say t times of a plus bk. Now this is some constant k dash, okay, and this is your variable, okay, which you are varying, okay. This gives you different input vectors, okay. So this I replace it as k dash and t, okay. So t times of k dash. Now tell me, when I am multiplying t, I'm sorry, I'm changing t, I'm getting different input vectors, right? On S, yes or no? This is the input vector. I'm getting different input vectors, yes or no? Tell me. See, T of S is talking about, see S, this line, okay. This line has multiple input points, infinite input points, yes or no?
Yes.
That's correct, sir.
Okay, so T of S, it is talking about the whole line. That is every possible point. It is talking about the image of it.
Yeah.
So T of S represents the image set for this whole line. Now, you know that S is represented as T of AB. T of AB. If you keep on changing this T as 1, so you will get one vector on S. If you take T as 5, you will get 5 times of AB again on the same line. So on changing T, you are getting different input points on the line S. Yes or no?
That's true. Yes, sir.
Okay. Now, okay. So I have written, you know that T of S is, this is the matrix corresponding to this linear transformation. So this is your matrix, and this is your input where you are feeding the inputs. So if I put one value of t, I will get one input. If I keep other value of t, I will get another input. So t is acting as a variable which helps me to get different inputs. Okay, yes or no?
Yes.
Okay, fine. So see, okay. So now what I did, I just did matrix multiplication of these. I did some manipulation. It would be t times of ta into C1 plus TB into KC1. So I've written TB into KC1, TA into C1. Now I've taken C1 as common. Okay. This is a fixed column decided beforehand because transformation was decided beforehand, right? We don't know anything, so we are assuming it. Now I am just collecting the terms. So C I have taken common out. TA plus TBK. Now I have taken T also common out. A plus bk. Now a plus bk are already constants, right? Yes or no? So I replace these constants with just another constant which represents these constants. Okay? Yes or no? By k dash. See, this is not important actually. I'm just saying that, just note for the time being. So k dash I have written here. Now what is the only variable part in this whole? In this whole, what is the only variable part?
T.
T. So if I change t, I am getting different input. So is this whole expression telling me the output for that corresponding input vector from t s?
Yes.
Okay. So isn't this again a scalar multiple of a column vector?
Yeah. Right.
Isn't the range a line? See, if you have a vector, column vector, and I scale it, so this tk is acting as a scalar in front of it. So isn't this a line? Tell me.
Yes, sir.
Okay, so it is a line. Now, okay, so now for third case also we have to check. So suppose these two columns were independent actually. Now I have written the general input vector. Again, I have multiplied it TA times C1 plus TB times C2. So I've got this. Now I have taken T common out as T common out. Then AC1 plus BC2. Now tell me, is this a vector? Is this a single vector? On adding these two vectors, I will get a single vector. This is not a linear combination because these A and B are fixed. They are not changing. So this will give you a vector, resultant vector. So this is basically T times of R. Is this clear? So again, in this case also, range is a line through origin. Are you getting this? Are you getting this? Hello? Am I audible?
Yes, sir. Right.
Okay,
Yes.
I don't think you are getting this. So let's move on to next question. I will explain it at the end, possibly through an example.
Sir, what is this number of questions that we get in this level? I mean, this difficult level.
No, no, see, this is not difficult. This is very easy. I don't know why you are. I mean, yeah,
Maybe because we lost the focus in between while you were teaching, so we couldn't get it. I mean, what is the chances that we get these kind of questions?
uh, okay, I think this is a very old question, so most probably not. But again, I cannot guarantee, right? But this is easy. See, if you think this will be easy. Like if you see, okay, I will explain it
So
at the end. Okay, from example.
when we are
Most
seeing as an example here, sir, it is very easy to understand generic math. But when we are about to solve in the exam, right? So we cannot able to generalize the holistic concept where we cannot focus that much. That's the only thing. Maybe it is complex.
yeah.
But
So yeah, the chances are not that high, but still, they are not zero also. Okay, so we will see this at the end also. Okay, in case you are, see, this is nothing but just as in manipulation. You will okay, let's move on. Okay, fine. If anyone wants to understand it he can point me to it at the end, okay, of the lecture. Okay, fine. Now this again. Now see, consider a vector space V with bases B, beta and gamma. Now T is a linear transformation from V to itself. Okay, so T is from V to V. It is written here such that T of V1 is equals to this. So this is the this is the image of V1 and this is the image of V2. Are you getting this? Okay. So now they are asking, based on the above data, answer the given sub-question. Find the matrix corresponding to T if gamma is used as basis for both domain and codomain. So just pick out gamma. Where is it? It is here. Okay. Now, both for domain and codomain. So domain. So what is your basis vectors? V1 plus V2, comma V1 minus V2. So what do we do first? We find the image of this and we find the image of this. Okay, so we find the image of this. Now, there is no way, they have not given us the specific linear transformation like this. How can we find it? But if you see that, they have given you T of V1 and T of V2. Okay, so we will utilize those. We need to find the value of this whole vector, output of this whole vector. So T of V1 plus V2 is equals to, you know that from linear transformation property, T of V1 plus V2 is equals to T of V1 plus T of V2. Now these we have in our hands. So these are given here. So V1 plus 2V2 and 2V1 minus V2. So V1 plus 2V2 from here and 2V1 minus V2 from here. So we add them, we get 3V1 plus V2. Now this is your output vector corresponding to this input vector. Now what is the next step? We express the output vectors as linear combination of basis vector of
Codomain
codomain.
with
And
gamma.
codomain also the basis vector is V1 plus V2 comma V1 minus V2. Right? So that's what I have done. V1 plus V2, V1 minus V2. So I have found the coefficients 2 1. Now for the second basis vector, t of v1 minus v2 would be t of v1 minus t of v2. I have the images. So v1 plus 2v2 minus 2v1 plus v2. So I will get this. This is your output corresponding to this input basis vector. Now I will express this output in terms of linear combination of the basis vectors for the codomain, which is again your v1 plus v2, v1 minus v2. So I found the coefficients. Now I just need to place them as columns. So 2, 1, so 2, 1, and 1 minus 2, 1 minus 2. So I've got my corresponding linear transformation matrix. Yes or no? Tell me.
Yes, sir. Yeah.
So can you see the answer here? So it is 2, 1 and 1 minus 2. Is this clear? Now can you tell me, is it an isomorphism?
Yes, sir.
How? You have to convert it
Sir,
to its.
yes, sir. So it is like we have we can find the determinant, and from the determinant we can see it scans R2, and it is also non-zero. So
Okay,
that's
so 1.5 and then subtracting it will give me 0 and minus 2.5. So then on this 1, 0.5, 0, 1. Okay, so this has two pivots. Okay, so nullity is 0 here. So this implies 1, 1. Now what is the rank? Rank is 2, 1, 2. So rank is 2, which is equal to the dimension of the, what is the codomain? What is the codomain? What is the dimension of the codomain? Can you tell me?
R2.
No, see, the codomain is not R2. It is from V to V. V to V. They have given you basis set. So you can count to find the dimension of the codomain. You can also count the number of elements present in the basis set. So this is first element. This is second element. So V2 is two-dimensional.
Yeah.
Is this clear? So rank is 2. This implies on 2.
So only one question, sir, here. Like we have the derivation is all very straightforward and it's understandable. Only confusion is here. How we get to know we need to find v1 plus v2 and v1 minus v2. So could you please give one hint, sir?
Where?
See, we are calculating the equivalent corresponding matrix by getting a v1 plus v2 and v1 minus v2. So how it was, where it is given by the question?
Just wait 1 minute. Let me do it clearly, okay? So see, they have actually given you two. First of all, the linear transformation is from V to V.
Yes, sir.
And they have given you two basis set.
Yes, sir.
Beta and gamma.
Okay.
But in the question, they are asking you to find the matrix corresponding to T if gamma is used as basis for both domain and codomain. Okay, so just write down gamma. So gamma is V1 plus V2 and V1 minus V2. And again for codomain also. V1 plus V2. V1 minus V2. Okay. Now what do? We find the images of these. Now, but we don't have the images of these directly given to us. Can you see it given anywhere? Can you see the images of V1, T of V1 minus V2 anywhere? T of V1 plus V2 anywhere?
No.
No, right? But we have been given images of these V1 and V2. So we can utilize these to find these by exploiting the properties of linear transformation. So let's see how. So we need to find T of V1 plus V2. So now I don't know how to find this. So, but I know that linear transformation has this property, that is T of V1 plus T of V2, right? Yes or no?
Yes, sir.
Yes,
This is
sir.
yes.
Similarly, I will write it here T1 V1 minus V2.
Yes, sir. Yes, sir. T of V2 minus.
So T, what is T of V1? T of V1 is V1 plus 2V2 2V2 plus of 2V1 minus V2 plus of 2V1 minus V2 plus of 2V1 minus V2. Now add them, you will get 3V1 plus V2. So this is your output image for this input basis vector. Now similarly here we will write V1 plus 2V2, which is this, minus of 2V1 plus V2. So I will get minus of V1 plus 3 of V2. So this is your output image of this. Okay. Now I need to express these vectors as linear combination of these two vectors, since they have given you that for both domain and codomain. So if you calculate it, again, if you are having difficulty in calculating it, you can just place A in front of this, V1 plus V2 plus B in front of this, then add them and then equate it on this side. You will get equations A plus B is equals to 3, like this. Okay, and you will get A, this is minus, right? A minus B is equals to 1. Okay, are you getting this? How? So V1 has A and V1 has B, so A plus B V1 is equals to 3 V1. So A plus B is equals to 3. Then A minus B, so this is, so A minus B is equals to 1 from here. So just calculate it, you will get A as 2 and B as 1. Okay, so now I'm going to directly write it. B as 1. Similarly, you will express this also in terms of V1 plus V2 plus of V1 minus V2. Okay, so from here it was 1 and minus 2. Again, you can find them on your own. So 1 and minus 2. Now you just need to place these as column. So 2, 1, and then these as 1 minus 2. Are you getting this? Are you getting this? Is this clear?
Yes, sir. Sir, here what is the significance of beta, sir? In the question they have given in the beta, right?
That is just for confusion. Okay. So see, they actually have given you the images of beta set, images of beta set, beta vectors from beta, see V1 and V2. But they have, in question they have mentioned gamma used as basis for both domain and codomain. Okay. So this is just a little bit of tricky question. Okay. Is this clear?
Yes, sir. That is where the confusion happens, sir. Otherwise, it was very straightforward question.
Fine. Okay. So is, okay. So see, whenever, okay, fine. Now you can convert it to its REF. It would be 1.5. I'm directly writing the REF. It would be 0 minus 2.5. So then 1.501. So how many are there? So rank is 2. 2 is equals to dimension of V. This implies onto. Nullity is equals to 0. This implies 1, 1. And these two implies isomorphism. Is this clear?
Yes, sir.
So it is an isomorphism. Yes or no? Is this clear? Is this clear?
Yes, sir.
Okay. Now they have given you a system of equations, so I'm directly writing the coefficient for this coefficient matrix: 1 3 minus 2 0 1 minus 1, then you have 1 1 0. So this is your matrix. Now coefficient matrix. Now they are saying what is the null space of it. So you can find the null space of A, right? I don't need to do that. I've already done it. Yes or no? Do I need to do that?
Yes.
Is it clear? Okay, so I've written DIY, which is do it yourself. Okay, because this is very basic. Like, is this clear? Is this clear?
Yes, sir.
Fine. Then I think I have done. Yeah. So I think I have converted it to. Okay, I have anyways done it. Okay, so it is here. So yeah, so I have completed it anyway. So this is your row echelon form. I have written the free variable, which is x3. I have I have assigned it a parameter. Then I've expressed the dependent variables in terms of free variables. So I got this as my null space, which is minus t1 t1 t1. Okay, so this is your null space. Now you know that nullity of A is 1, and as soon as for any square matrix, if nullity is non-zero, this implies determinant will be non-zero. But if nullity is 0, this implies determinant will be
0.
0. Okay, so we will use this here because they have said let B be a square matrix. Now we don't know what is this matrix. They have given us no information at all about this matrix, but we know some information about A matrix. So they are asking what is the smallest value of nullity of BA that could take nullity of BA. So we will use that here. So I have written a B matrix, don't know its elements. A matrix, we know everything about A. Okay, we know everything about A. Now BA would be what would be the order of BA matrix? Tell me. What would be the
It
order
will
of
be
BA?
3 cross 3.
Exactly. Okay, so it would be 3 cross 3. Now I've written rank of BA plus nullity of BA is equals to 3. This is for sure. You can write this. Yes or no?
Yes, sir.
Now you know that what is the determinant of A? Tell me. What is the determinant of A? You know that nullity of A is 1, which is non-zero. So determinant would be
Zero, sir.
Non-zero.
I think, sorry, I've written it wrong here.
So you written it like det nullity is not equal to 0, then det is 0, sir.
Yeah, exactly. This should be correct. Okay. So tell me, is nullity 1 for A? Is nullity 1 for A?
Yes, sir.
Yes, sir.
Sorry, is nullity for A 1?
Yes, sir.
So that means determinant of A should be 0.
Yeah.
Now tell
Yeah.
me what would be the determinant of BA? It is determinant
0.
of B. Determinant.
0.
It is 0. Now this tells you that determinant of BA is 0. So that tells you that nullity should be non-zero.
Three.
Non-zero.
Right?
Non-zero.
So nullity is non-zero. That is for sure. So I've written it here. Determinant of A is equal to 0. This implies determinant of BA will be 0. This implies nullity cannot be 0. Okay. That is nullity is non-zero. That
Sir,
is for sure.
over here, if determinant of B is not equal to 0, and determinant of A already we know it is equal to 0,
No.
then
How can it be possible? You know it from this only. If determinant of A is 0, then determinant of BA will definitely be 0 from this. Taking determinant of BA would give you determinant of B into determinant of A, which will be 0. Okay. Is this clear?
Can we say that? can you say that the determinant of A is 0 means there is no dependent variable, only independent variable is there. So,
no,
because
see,
nullity is positive, right? Greater than 0.
see,
So
since
nullity depends on
nullity of A is non-zero, that you can see it is 1 here.
correct. So
That means a
nullity
free
is non-zero means it means that it's all independent variables, right? So it's
no,
nullity
not all
represents
independent variables. See, if nullity is non-zero, I'm not saying that it is 1, 2, or 3. I'm just saying that it's a non-zero number. It could be 1, it could be 2, it could be 3. So we cannot tell how many free variables are there or independent variables are there.
correct. So there are many independent variables are there. There is no dependent variables.
No, that we cannot say that, right? Because I'm just saying that it is non-zero. I'm not specifying whether it is 1. If it is 1, then it would mean that there was one free variable. If it was 2,
I
go on. Okay. Okay, so yeah, you know that determinant of BA is also 0. This means that nullity must be non-zero. So nullity cannot be 0. I've written it here. Now if I take B as identity matrix, okay, I've just taken it randomly. What would be BA? BA would be A itself. So what would be the nullity? And it is asking you, if you see in the question, what is the smallest value of nullity? It can be 1, right? After 0, since it cannot be 0, the next smallest in line is 1, then it is 2, then it is 3. So if they have not given you any information about B, so I can take it as any random matrix. So I've taken it as the simplest matrix which I could think of as identity matrix. So BA would give me A itself. So I know the nullity of A, so which is 1. So nullity would be 1. Is this clear? Which is the smallest nullity? Tell me.
Yes, sir.
Are you getting this?
Yeah, sir.
Yes, sir.
Are you really getting this or just nodding along?
Yes, sir.
Okay. Okay. So it is 1. Okay. So now fine. Okay. So another such example. So let's see. So they have given you, consider the vector space V is equals to A, B, C, A such that C is equals to A plus B. Now, this is the example which I was talking about. You have a condition given here. So what you will do, you will replace this here. It is already expressed in terms of other variables. So I've expressed it here. So now, yeah, I've expressed this general element here. So A, B, A plus B, A. So I will do it again. I will try to find the basis for V. How do I find it? The same method which I told you before. So these are your basis vectors, basis elements, okay, which are basis matrices for V. Now what is the dimension of V? V is what is the dimension of V?
2.
2. Okay, V is 2-dimensional. Now, okay, so I have basis vectors. Now see, T is from V to R4. So I have in my hands the basis for your domain. Okay, I have my basis vectors. Yes or no? Yes or no?
Yes, sir.
Yes, sir.
And for R4, I know everything. I can just take the standard input basis in standard basis vector, right? So now they have given you the linear transformation definition. They are asking choose the correct option. T is onto but not 1 1. Okay, so again we need to get hold of the matrix corresponding to this linear transformation. So I've tried to find the images of the first basis vector of B. Okay, so according to this, what is the definition? A, B, C, A plus B minus C. So A 1, B 0, C1, fine. Then A plus B minus C. A plus B minus C. So 1 plus 0 minus C, so 0. So A0, B1, C1, then A plus B minus C. So 0 plus 1 minus 1, so again 0. So I've got this. Now I've placed them in the matrix as columns. Again, I don't need to express them as linear combination of standard basis vector for R4, right? Because you know that you will get the same vector. Yes or no? Yes or no?
Yes, sir.
Now you have the matrix in your hand. Can you tell me the nullity, 1, 1 and on 2 nature of it? So nullity, you can see it as non-zero. Okay, if you convert it. So you will get a matrix like this, 0, 1, 0, 0, 0, 0. Okay, so you will see that nullity is 0. Okay, so this will imply that it is 1, 1. Then column space, sorry, rank is 2, and which is not equal to the dimension of the codomain 4. Yes or no? So is it
Yes.
on 2? It is
Yes,
not,
sir.
not on 2. Okay, so it is 1, 1 but not on 2. And now there are a few more options. Okay, so okay, you can see that nullity is 0 here, but it is saying null space of T is a two-dimensional subspace, so this is wrong. And this is wrong. What about this range of T? Now range is span of the independent columns present in it. So how many independent columns are there? 2. So span of C1, C2. So range of T is a two-dimensional subspace of R4. Is it true? Yes or no?
Yes.
Okay, so it is true. Fine. Then yeah, I think okay, so we are already on week 6. Okay.
Okay,
Okay.
sir.
So
So for one onto function, we check that the rank of codomain and the rank of corresponding matrix are equivalent for one to one. What we check
sorry, where?
here, here we check like the dimension of the A matrix and the dimensions of codomain were not matching, so it was not onto.
Yeah.
And how we came to the conclusion for one to one.
1 to 1, see nullity is 0. That is no free variable is there. You can see that both columns have pivots. This is
Okay,
the
if
pivot
we have
present
a
in a
free
column.
variable, then it will be one to one.
Then it will not be 1 to 1. But since there is no free variable, that's why it is
Okay, if
1, 1.
nullity is 0, then it's one to one, and if nullity is not 0, then it's not one to one.
Yeah. So nullity, see, when nullity is 1, it means that there is one free variable. When nullity is
One free
0, it means
variable.
that there is zero free variable.
No free variable. Yes.
Okay, fine.
Okay.
Okay, so question 12. Now, let V1 denote the vector space solution of Ax equals to 0. Again, I think we have seen this question. So V1 is null space of A. So this is continuation of that only, just that it is in week 6. Null space of A. Now V2 is null space of B. Okay, denote the vector space of solution of By equals to 0. So it is the exact same question, just there is another part to it. Now it is saying let S be a linear transformation from V1, that is the null space of A, V2 null space of B, if M cross N is the order of the matrix D of the linear transformation corresponding to S with respect to some ordered basis alpha 1 for V1 and ordered basis alpha 2 for V2. What is 2M minus 3N? So first of all, I have written this V1 from the previous questions. Okay, V1 is this. Okay, this is the continuation to the question we have discussed before. So this is V1, this is V2. Now you can see that V1 is a one-dimensional null space. V2 is also a one-dimensional null space. Now S1 is a linear transformation from V1 to V2. Now okay, alpha 1 is some ordered basis for V1. So what I did, I took alpha 1 as -4 -4 3, which is 4 times of this vector. Okay, I can, since you know that bases are not unique, I can just scale this. I could have taken -4 by 3 -4 by 3 and 1, but I just, for simple calculation, I took it as -4 -4 3. Okay, then, and alpha 2 is an ordered basis for v2. So this is the basis, since there is only one basis vector. So my 1 -2 1. Now see, this is your domain, which is represented here. So this is your v1, and this blue line is your v2. Now you don't know the specific definition of it, s. Okay, but you know that if I input a vector, I am getting, since my codomain is this line, this blue line, I know that my vector will lie on this line. Yes or no? Yes or no? Tell me. If I input a vector from this line, since my codomain is this, I will have a output in my codomain only, right? Yes or no? Yes or no?
Yes, sir.
Yes.
See, what is your codomain? It is your v2. So if I input vector from v1, I will definitely get my output in the codomain only, right?
Yes,
That's
sir.
is v2. So I have written it. I know that it will lie on this line only. So I have written it s of 4 -4 -4 3. That is your basis vector, is equals to k times of 1 to 1. Although this was not needed. Okay. Now I have placed this as a single column. So you can see that the matrix is actually a 1 cross 1 matrix. So what is value of m? It is 1. What is value of n? It is 1. So 2m minus 3n is nothing but -1. Is this clear?
So how come the matrix is 1 cross 1?
Yeah, see, it is a real number. You could say that it is a matrix, right? One row, one column, so one element basically. So
So could you
see,
please explain this again? Like this part, the matrix part.
okay. So see, what do we do when we express an output? We do this, right? A plus basis vector of codomain plus b. Then we take these and place them as columns, right?
Yes, sir.
So I did the same thing. So since I have only one basis vector, I got only one output. Now this one output on being expressed will be okay. So this we will get this, and this will be again. I am expressing it as this vector would be 1 2 minus 1. So 1 2 minus 1. So I place this as a
Okay, sir.
column.
Got it, sir.
Yeah. So this is 1 cross 1. Is this clear to all
Yes,
of
sir.
you?
Yes, sir. There's
Yeah.
only
So
one coefficient.
yeah, exactly. So m is 1, n is 1. So they have asked you to find the value of 2m minus 3n. So 2m minus 3n is -1. Is this clear?
Yes, sir.
So answer here is -1. Okay. Now, yeah. So this is a direct question. Okay. I think this is a part of previous question or what? Hmm. Okay, so I think this is a direct question. Okay, yeah. So I think this is the last question. Okay, there are more questions left. One more question. So let's see ninth question. Okay, so this is very easy. You can do it. Okay, nothing different. Okay, is this clear? Is this clear?
Yes, sir.
Okay, let
Yes, sir.
yeah.
Yes, sir. It was good.
Okay, so let's see ninth question. So again, they have given you a arbitrary vector space of matrices. Okay, A, B, C, D. Then again, they have given you this condition. Okay, so this I have already explained that what you do is you try to express one of the variable as in terms of other variables. So what I will do, I will express I think we won't need, yeah. So I have expressed here B in terms of A, C, and D. So B is equals to C plus D minus A. Then I will replace it here. So I've replaced it here. Then I will express it as a linear combination of matrices. So these are your basis matrices. So I've written basis for V. So these, okay. Then I found the images of these. Okay. So I have, okay, again, they have not specified the, they have not specified the transformation. So I've just written some arbitrary vector. I don't know what is the answer. Okay, but just to show you, now this would be expressed as linear combination of basis vector for your codomain. What is your codomain? Codomain is R2. So expressed as a linear combination of 1 0 and 0 1. Okay, so now what I am saying is that matrix will be 2 cross 3 matrix. Yes or no? Although we could have directly written it from here only. We know that V is 3-dimensional. V is 3-dimensional and R2. So what will be the matrix order? 2 cross 3. Yes or no? What will be the matrix corresponding to this? It would be a 2 cross 3 matrix.
Yes, sir.
Okay, so I don't know why I did this. So 2 cross 3 matrix. Now they have said that if T is onto, what is dimension of kernel of T? Now you know when is T onto? When rank is equal to dimension of
Dimension of
codomain. So
codomain.
what will be the rank? It will be 2. Yes or no? So they have given if T is on 2. So this means that they are hinting that rank is 2. Then find the dimension of kernel of T. Now what is dimension? What is other name of for kernel? It is
Nullity.
Nullity.
Null
no
space.
null space. Null space. Okay. Nullity is the dimension of the kernel or null space. Okay. So what is the dimension of the kernel? So what is the dimension of the null space? It is nothing. They are asking you the nullity. So you know rank is 2. You have to find nullity and you know what is n? It is 3. So rank plus nullity is equals to 3. So 2 plus nullity is equals to 3. So 2 plus nullity is equals to 3. So nullity is 1. Dimension of the kernel space. Is this clear?
Yes, sir.
Yes, sir.
Okay, sorry.
So
Yeah,
instead of kernel of T, they ask image of T. What is the function?
sorry.
Instead of kernel of T, they ask image of T.
Image of T, see, image of T is nothing but the column space. So basically, if they had asked you the dimension of the image of T, it would be 2, which is rank. Because they have all, which is rank. So it would be 2. Dimension of image set. Column space dimension. See, I've written it at the very first point.
So I have one doubt, like how we came to know that V is like in R3 or V is 3-dimensional.
Okay, just wait 1 minute. So see, I have written it here, range, image set slash column space. All these are synonymous. Okay, synonyms. Is this clear?
Yes.
Kernel, null space, both stand for same thing. Range, image set, column space, all stand for the same
So
thing.
can you explain what is an affine subspace?
Affine subspace, okay, if we have time. Okay, so basically see, affine subspaces are nothing but linear translates of subspaces. You know that subspaces always pass through origin, but affine subspace need not pass through the origin. So that is the only difference. So that's why we say them as linear translate. Okay, we fine. If I have time, then I will explain it. I think we are already past the time, but still, let's complete whatever is there. Okay. Uh, where were we? Okay, yeah. Here we are. Okay. So question 10. let T be a transformation from R2 to R3. Again, they have given you the transformation. You can find the matrix corresponding to it. It would be a 3 cross 2 matrix. Yes or no? Yes or no?
Yes, sir. Yes, sir.
Now they have given you that this is your basis set for domain R2 and this is your basis set for codomain. So you will find the matrix corresponding to these two, okay, bases, and they have said that this is equal to A, B, C, D, E, F, and they have just asked you to find what is A plus D plus E. Okay, so you will equate this to this after finding it, and then you will find A plus D plus E. So I have done this here. So see again the same thing. So yeah, so this is your A matrix. Okay, so they have given you R2 bases, they have given you R3 bases. I found the images for R2 bases vectors. So these are the images. Now I have expressed these images as linear combination of these vectors. So these you need to find. Okay.
Sir,
Now
is there any shortcut to get this coefficients? Example 204 is to be converted to this one, right, sir?
So these coefficients you say?
Yeah, yes, sir. Because
So see, just take them as A 111 plus B 110 plus C minus 100. Now you add these three vectors, you will what you will get? You will get A plus B minus C, right? Then A plus B, then see this is 1 1 0 0. Okay, what you will get? A, right? This you will get. Now you will equate it to 204. So 204. So this will give you A as 4. So see A as 4. So here you can see 4. Then B is A plus B is 0. So B is minus A. So B is minus A. So minus 4. Okay. Then C is A plus B. So C is minus 2. I think sorry, it is 2. A plus B plus C. A plus B minus C is 2. So C would come out to be minus 2. So I place it here. Are you getting this? How you'll find it?
Sir, can you show the question once?
Okay. This 10th question. See, they have just asked you what is the value of this expression. They are saying the matrix which you will find, you will equate it to this given here. And they are just asking you A plus D plus E. Are you getting this?
Yes, sir.
Okay. So see, this is the matrix which we got. Now you know that this is equal to A, B, C, D, E, F. Now what is A, D, E? So A is 4, D is 0, E is minus 2. So you got 2. Is this clear? Is this clear?
Yes, sir.
Now they have in 8th question, they have directly given you the matrix. They are asking you what is the nullity of matrix A. You can calculate it. Okay, they have given you everything. Now which of the following option is true? You can again, so nullity here is 1. You can see it is 1. Now what is rank? Rank is 2. What is dimension of codomain? It is 2. So is it on 2? It is on 2. Is it 1 1? No, because it is nullity is
No, it
non-zero.
is not 1
So T is on to what? So I think T is on to. T is on to, but not 1 1. So this option is wrong.
Sir, one question, sir. Here you mentioned as a nullity as a 1, right? So as in the row direction, when whatever after you are doing, still we in both columns we have we have pivot elements, right, sir?
Yeah, no,
And
but
third
there are three.
column,
There is third column. So this is not a pivot. So pivot is always the first non-zero element. So see, for this column to have a pivot, there need to be a third row, but there is no third row. Are you getting this?
Yes, sir. Yes, sir. So I
Okay.
always thought it should be in a row. In that row, because in this lectures also they have mentioned in a row it should have one non-zero element. Means pivot element, non-zero pivot. So first row also having one and second row also having one. So I thought that way. But after this one, you should check it in the column, and that column should have a non-zero pivot element. That's
Yeah.
okay.
Okay. So next is this third question. Now, okay, just wait. Third question says, okay, so third question is not related to this. So they have given you this linear transformation. Okay, so you can see that this is your input vector. So input vector is from R3. So input domain is R3. Then what is your output? Output codomain. So see the comma. So there are two elements. So your
R2.
output is R2. So I have just assumed everything to be standard basis. So I have found the images according to that. Okay. Uh, just wait 1 second. Okay, 10. Like, 1 minute. Is this part? Okay, this is a sub question. Uh, okay, yeah, this is a good question. Fine. Okay, so T of 100 is, what is T of 100? Okay, so here what you need to do is, here you need to find the images of it, T of 10. But I have not been given a linear transformation, at least not explicit. So it has lots of variable. Okay, so what it is saying is, you find the linear transformation definition. It will come out to be something with 5x plus, and then you equate these terms here. Then you will get m, n, s, p, q, r, all values. So see, you know that these are the vectors correspond in front of these vectors, right? Yes or no? And these numbers are in front of these vectors. Okay. So to find T1 of 00, I am using these. So T of 100, to find the image of T100, I am moving in backward direction. So you know that it would, T of 100 would be 1 times of 10 plus 1 0 times of 1. Yes or no? That's how that matrix came, right? 10 from here. Yes or no? Tell me. That's only these matrices came, right? 10. Then see, there is -1, 2. So you know that for this t of 0, 10, it would be -1 times of this 10 plus 2 times of 1. So I've written it here. That's only these matrices came, right? Yes or no? This matrix came in this fashion only. So I'm backtracking the algorithm.
Okay.
So see, 0 times of 10 plus 3 times of the 1. So I got the images of each of these. Tell me, yes or no? Yes or no?
Yes.
Are you getting this? Okay, so
Yeah.
I'm backtracking. So generally what I do, 10, 10. So I place them as column. 1, 1, 2 places them as column. 0, 3 place them as column. Okay, so I got the transformation. Now I'm just moving in backward direction. So 1 times of, I know it would be 1 in front of 10, then 0 times of 1. So I got the image adding these two vectors. So this would be 1, 0. Similarly, I will get the image of these. Then similarly, I will get the image of this. Now, why I'm doing this? You should know that if you know the images, of any basis set for the codomain, any basis set for the domain, sorry, then you can explicitly calculate this type of definition for the linear transformation. Okay, so that's what I did. I found the images of three basis vectors. Now, how to find this definition, this sort of definition? What I do is I take the general element xyz. I express them as a times of these basis vectors 1 0 0 0 1 0 and 1 1 1. So I've expressed them. Then I added these and I equated that to xyz. So I calculated c as z, b as y minus z, a as x minus z from here. Now I am expressing it as this x minus z. So I've substituted a as x minus z, b as y minus z, and c as z. Okay. Now what I am doing? I am applying the linear transformation on this general vector. T of x, y, z is equals to this whole. Now I exploit this property of this. So this is x minus 2 will come out. T of 1 0 0 plus y minus 2 T of 0 1 0 plus z of T of 1 1 1. Now I know these images. So I know these images from here and here. So I substitute them here. So 1 0 1 2 3 3. Now add these and you will get this definition. So this is on solving it. This is x plus y plus z, 0x plus 2y plus z. Now this has been equated to which? Mx plus ny plus sz, comma px plus qy plus rz. So what is your m? M is 1, n is 1, z is 1. Am I audible?
Yes.
Hello? Okay.
Yes, sir. Yes, sir.
P is 0, q is 2, r is 1. So I have written them down and I have calculated the expression which they are asking. M plus n plus s, so 1 plus 1 plus 1, 3 minus 3 times of p plus q plus r, 0 plus 2 plus 1. So this is minus 6. Is this clear? Is this clear?
Yes, sir.
Okay, so again, this was a good question, at least the third
So
part.
how we found mn?
Mn, so see, here they have, okay, is this part clear how we achieved this? Is this
Yes,
part
sir.
clear? Now they have given us a general representation. So T of, see, they have given you if T of x, y, z is equals to mx plus ny plus sz, comma px plus qy plus rz. So I can write it here. So now just equate these. So you have 1 here, sorry, 0 here. I think no, sorry, 1 is, it is 1 here. So this is 1. Okay, I actually draw a circle here. So this is 1, m is 1, n is 1, s is 1. What is p? P is 0 because there is 0 here. Q is 2, r is 1. So I wrote them down and then I calculated this expression. Is this clear?
Yes, sir.
Okay, so the important part in this was finding the linear transformation itself. And before finding linear transformation, you need to have 3 images of basis vectors. Okay, so that's why we backtracked it from this matrix. That's why this was given to us beforehand to calculate the images of these. Okay, that's why they had given it beforehand to backtrack to get the outputs, then expressing the general element as linear combination of these basis vectors, finding these coefficient, then exploiting the property of linear transformation, then substituting those outputs, images which we found earlier, then adding them and getting the corresponding linear transformation. Is this clear? Is this clear?
Yes, sir.
So I'm going to just clear this out. Okay. Okay. Uh, okay. I hope all this was clear, right? So
Sir, I
any other
have
doubt?
a doubt.
Yeah.
Sir, in general, I was confused with this linear transformation of this. We transform the vector into R2 to R3, right? For example,
Yeah.
we are taking the basis of R2 and basis of R3 and we are doing a linear combination.
Yeah.
That one is confusing for me.
Okay. Okay.
For
Fine. So
example, in this question, we have beta and gamma. I don't
yeah.
know which one I have to take and which one to
So see.
combine linearly.
See the beta elements of beta are they vectors from R3? So they are obviously for your you know domain. And for gamma you have 1 0 which is a vector from R2. So this is your domain for your codomain. Okay, are you getting this?
Oh, yes, sir.
See, they have given you with respect to ordered basis beta and gamma for the domain and codomain. So there is one respectively word here, right? So whichever is mentioned first will be mapped to this domain and the second one will be mapped to codomain. That's why they have written respectively. Is this clear?
Yes, sir.
Okay, so I think we will end this meet here. We have covered most of the week 5 and 6 PYQs. Week 5 we have covered completely. Week 6 we have also covered a good amount of it. So let's end the meet here then. So any other doubt? So yeah.
Sir, in initial session when we are generally we were summarizing the week 5,
Yeah.
that was really helping, and with that knowledge only we were able to get your all the solution solving.
Okay.
And there we have skipped to two part because of people want to skip this particular explanation where the two part is was the range and kernel. So could you please give some
Okay.
insights?
So range.
Let
So
1 minute.
range.
1 minute. Let's take a note. Yes.
So range, column space, and image set all stand for the same, okay, same set. So range, column space, image set. So how do we find the range and image and column set? Sorry, column space. So what you find A
Yes.
corresponding to T. Okay, find A corresponding to your linear transformation. Okay, is this clear? Well, first step is this.
Yeah.
Then convert A to REF. Okay. Then third step is column space is span of those span of okay, columns which have pivot. Okay. Okay. So one more thing. See, I will give you an example. So you have to note it down for yourself. Okay, I cannot write it down. So see, when you convert it, when you convert a matrix. So see, your matrix is this. Suppose this is your matrix corresponding to this linear transformation. Okay. Then we convert it to its REF. After REF, it looks like this. Yes or no?
Yes,
Yes
sir.
or no? Now, which columns have pivots? This first
First and
column
two.
and
Yeah.
second column.
Yes.
Now, what you have to do, you have to move back to the original matrix.
Yeah. For to get the column
Okay.
space. Yes.
Now see the first column and second column. Just note them down and place them inside this span. Columns. So columns in original matrix corresponding to columns in REF which have pivots. Okay, so columns in the original matrix you have to pick columns in the original matrix. So this is very important. Do not pick it from the REF matrix corresponding to columns in the REF which have pivot. So if first column have pivot in the REF, then you will pick the column first from the original matrix and place them here. So span of C1, C2. So okay. So here I will write it here. So just for this, so let me write the range. Okay. So range here or column space is span of, tell me, what should I write here? What should I write here? Which columns have pivots? First
and
and
second.
second. So I will move back to my original matrix
1 0
and
0
write them as 1 0 0 and
1
1
minus
minus 2
2.
2. Now this is one way of writing the image. They could write it like this also. So x, they will write a variable in front of it, x 1 0 0 plus y, another variable in front of this 1 minus 2 2, and they will add them and you will get this x plus y, then x minus 2y and 2y. They could write it like this. Okay, so this is your range. Is this clear?
Yes.
Is this clear? Is this clear?
Yeah, yes, sir.
Now, when would range have been equal to the codomain? When all three columns had pivot, right?
Yeah.
So okay, because then only it is onto, right? Onto is when range is equals to codomain. So that means rank is 3. That means all three columns should have had a pivot, but they don't have in this case. So range is a subspace of your codomain. Okay.
Can you please
So
explain here, sir? See, we solve this column space and we converted to x plus y and minus is a minus 2 and then y, 2y.
they could have taken a also. See, these are just variables. You will add them in, you will get this general vector. And then they will, what they will say? That range is this. Range is this set.
Yes, sir.
X plus y, x minus. So this is C. If you see that, this is basically just reverse of what we do when we want to express a general element as basis, sum of basis vector, right?
Yes, sir.
Okay, so that is only the opposite. Nothing but the same thing. X minus 2y, then 2y, such that x comma y belongs to real number. So they can give you it in this form, they can give you it in this form. So you
Yes.
can write it in any form.
Yeah.
So this is range. Now see, sometimes there exists a case of multiple choice option. In that case, usually the case is when your when your f is onto. So okay, just forget about it. Okay, no need. So, but just see this thing. Okay, so you know how to find the column space. Now, okay, what was left? Null space is easy, right? Null space you have already seen it quite a lot of time in today's lecture,
Yeah, yes.
right? Okay,
Yes.
so we have these are the only types of questions which are asked, at least from week 5 and 6.
Okay.
So
Sir,
if you know,
actually, as we are discussing, sorry to interrupt, sir.
yeah,
This,
yeah,
if we are going from the order like a rank, nullity onto, it was very straightforward and it is very easy to understand. When
yeah,
you are saying range is equal to codomain, that question still I'm not able to understand, sir. Range we
range
are
is,
able to calculate. After
yeah.
that, how we can correlate to codomain?
So see, the thing is, you can see that uh, here you see that range is a two-dimensional subspace. Tell me, is it range is that? See, what is the dimension of range? Are there only two vectors?
Yes, sir. Only two vector.
So this tells you that this range is two-dimensional. Now, what? See the codomain of this. What is the codomain?
Is it okay? Okay, R3.
T is from
R
R3 to R3.
three. Yes,
So
sir.
your codomain is three-dimensional.
Yeah.
That is this is your codomain. That is your R3 is your codomain, and inside it, range is a two-dimensional subspace which lies like this, which is a plane. So you can see that plane is a small part of R3. So you can see that here range is not equal to codomain. So this is your range.
Got it, sir.
Okay, so here range is not equal to R3. It is a two-dimensional plane because you saw that column space has only two vectors in it, span of two vectors. Here. Here. Are you getting this?
Yes, sir.
But when we have three pivots, then rank becomes 3, then it becomes on 2, right? Because rank on becoming 3 becomes equal to the dimension of the codomain, which is 3 here. Then there would be 3 vectors here. Then it would be a span of 3 vectors, which would be a 3-dimensional plane. So in that case, it would be the whole of R3. Are you getting this? Are you getting this?
Yes, sir. Clear.
Okay, so we will end this session here. So if you remember this part, then you can do everything. Okay. Okay, fine.
Sir, can we get this PDF in the discourse?
Yeah, definitely. So this will be uploaded by my instructor. So he will upload it. Okay. So any other doubt? Anyone?
So this will cover both week 5 and 6, right, sir?
Yeah.
Still we have something from week 6.
In the
Okay,
discourse, you will upload it, is it? Where you will upload actually this?
Instructor sir will upload it. There is a Google Drive and you can access it from there. So let me see.
Okay.
Yeah, so we have covered everything. Okay. Now one more thing. Can you tell me basis for range would be from this example only? Tell me what would be the basis for range? Basis for range would be these two elements, right?
Yes, sir.
Okay. Okay, fine. So now you know everything from week 5 and 6. So I will end this meet now. Okay.
Thank you so much, sir. Thank you.
Yeah.
So when will we get the PDFs?
So I think by midnight you will get this PDF.
Okay, okay. Thank you, sir.
Okay, so
Where it will be uploaded, sir?
It would be uploaded in a Google Drive owned by the admin. So by the instructor, sir. So he will upload it. Okay. So by today's midnight you will get. Fine. Is this clear?
Okay, sir. Thanks.
Thank you, sir.
Okay, just wait 1 minute. Okay, fine. You can leave.
Sir, tomorrow what time, sir, session?
So tomorrow I won't be taking session. There is another TA sir who will be taking the session. Okay, so yeah, same time, 8 to 10.
Okay, sir. Thank you.
Okay. So were you all able to understand?
It was really good, sir, actually, to be honestly. And if we can, since we are running out of the time, that's why you rushed. Otherwise, the initial explanation was really nice.
Okay, fine. Thank you. Okay. Okay, you can leave the meet then.
Thank you, sir.